because I do want to be able to share this with people who aren't here. All IP addresses are logged. That's just, to protect everyone here. And so that's pretty much all I need to say about that. Your exam obviously is Tuesday. You're going to be in the gym. I believe it's a morning. What's that?
I don't want it to be in the gym.
Yeah, unfortunately, that's the only way to get is proctors, enough proctors there to be able to do it in a seamless way. So I hope that doesn't adversely affect how you perform. But it's going to be at 7:45 as far as I know. I believe it's a morning exam. There'll be a list on the board basically showing where you sit. And you're going to come in, find where you sit. There'll be your Scantron will be on the table already, so it should be pretty quick to get settled. Just a couple of things. I think you already figured it out, but there are just a couple of things about this particular technology that you need to be aware of. You probably already know that the chat window is there, but there's a little, if you look very closely, little window there that says chat. If you want to see what people are saying to each other, or if you want to talk to each other, you just drop that window down. If you look to where it says attendees, that's everyone who's here at the moment. When I took this screen capture, I was the only one present, so that's why you can't see everyone here. Just one more thing. If you want to say something to someone in particular, like you don't want the whole group to see it, what you need to do is you need to change the to part. If you can see where I am on the screen, where it says to, you need to change that to the person you want to type your message to. Obviously, I'll be asking you questions. I think it would probably be better if you send your answers to me personally rather than to the entire audience. That way, if there's someone who's not finished with the problem, they can finish without being influenced by anyone else's answer. What else do I need to do? Okay, so as I said before, things that you're going to need for this activity, you're going to need reference tables, calculator, pen, pencil, something to write on, just so you can make this as effective as possible. Looks like somebody just joined us. I don't know who that is. We'll find out soon enough.
I think it's Hayla.
What's that?
I think it's Hayla.
Oh, okay. All right, good. Okay, so the first thing I'm going to do before we get into actual questions, I just want to go over some important things, specific things that key things that types of questions that you could be asked. I'm going to start with a reference table type questions. Obviously, a lot of the questions that you'll be asked will be based upon the reference table, and I'm just going to go over some of those questions that you could be asked. So obviously, there's different reference tables. There's table A to begin with. Something to take note of, if you ever forget what standard STP is, it's here. It's 101.3 kPa or 1 ATM or 273 Kelvin. The other reference table that's really important on this page is the table B, and that's the physical constants of water table. Types of questions they could ask you there, they could ask you heat type questions, right? If they ask you to calculate heat based on the absorption or release of water, you'll be using one of three possible formulas that are shown on the screen. Those are probably the two most important reference tables on that page. So I have a couple of questions here where they could ask you. The first one says a gas occupies a volume of 5 liters at 25 degrees Celsius and 101.3 kPa. What's the volume of the gas at STP? So how would you work that out? Anyone have any suggestions, or just actually maybe it's probably better if you try to figure it out yourself. And what we'll do is we'll share out after you have some time to actually figure it out. Haley, we just started, so we just started discussing one of the reference tables, and these are questions that are based upon those reference tables. So if you have an answer for that question, just send it to me. That way no one else is influenced by it.
What is that?
Hayla.
What?
Oh my god. Hayla, we can literally hear you move around. Like, your mic.
Oh yes, I'm sorry, Haley. Your mic is not muted. If you'd like me to mute it, I can. Just let me know.
No, we can mute our own mics.
Yeah, you can. Okay, that's fine. You can do that too.
I don't know how.
Okay, I mean,
It's the
I can.
green mic.
There's a little where it says
Oh, I
attendees.
see.
You can just click it. Would you like me to mute it, or you want to leave it unmuted? Okay, she muted it. Okay. So, do we have an answer yet?
I have no
Hold
idea how
on.
to like start number one. Like, can I
Okay.
get a hint?
So
Wait, do you
it's a
have
gas.
to-
It's a gas law problem, obviously. It says a gas occupies a volume of 5 liters at 25 degrees Celsius and 101.3 kPa. What's the volume of the gas at STP? So you need to know that STP, again, is 0 degrees Celsius and 101.3 kPa. So what they're not telling you here, by the way, excuse my handwriting. I'm using a digitizer for this. But what they're not telling you here is that pressure is constant. And so for any type of problem, any type of gas law problem where something is constant, you simply cross it out of the combined gas law formula. So combined gas law formula is P1 V1 over T1 equals P2 V2, V2 over T2. And so because pressure is constant, we're going to cross out pressure. You do have to interpret some information that's in the problem. It says the volume is 5 liters. So that's your initial volume. That's V1. The reason I know that's V1 is because they're asking you for the volume of the gas at STP. So that's a second volume. They're asking for V2. That's a question mark. The initial temperature here, T1, is 25 degrees Celsius. But the one thing you have to remember about gas law problems is that they cannot be worked out. They cannot be worked out in Celsius. You have to make sure you work it out in Kelvin. So what we're going to do here is we're going to solve this for V2, and simple cross multiplying will allow you to calculate that. So that's V1 times T2 equals V2 times T1. Oops, come on. And so since we're solving for V2, this is just V1 times T2 over T1. If I've done that right. Come on. V2. And you're just going to plug in. So the initial volume was 5 liters. And the second temperature in the problem, that's the temperature of STP. So that's 0 degrees Celsius. So we're going to convert that to Kelvin by adding 273. So that would give me 273 is my second temperature. Come on. And the initial temperature, if you look back at the problem, it says 25 degrees Celsius. So that's 298. And you would just go about, multiplying the top, dividing by the bottom. I'm not terribly interested in the answer here because I think you guys know how to use a calculator. But the one thing you need to be aware of here is that this answer should only have 1 sig fig once you've calculated it. On the other hand, if they don't ask you for to round it to sig figs, then you can leave it unrounded. But again, just to be consistent with what we've done all year, you would round this to 1 sig fig, whatever the answer is. Did anyone actually work this out? I don't have a calculator right next to me.
5 is what I got. Rounded to 1 sig fig.
Oh, okay.
Yeah,
So what literally comes out of the calculator?
4.5805.
Okay, yeah. So in this case, it actually, believe it or not, makes more sense not to round it. The reason I say that is because if you round it to 5, it appears as though the volume didn't change. And we know that the volume should change here. And why do we know that, by the way? Why do we know that the volume should change?
Because other things are changing.
What's that?
Other things are changing.
Well, the volume in the problem, it went down, right? It went from 25 degrees Celsius to 0 degrees Celsius. So if I'm sorry, the temperature went down. So if the temperature goes down, the volume should also go down. That's because the relationship between temperature and volume, if you recall, it's a direct relationship, right? So if temperature decreases, volume should also decrease. So we would expect that the volume would be less than 5. And of course, if we actually calculated, it is. All right, so that's one question that they could ask you, from the reference table. The second question that they could ask you from the reference table, or another question I should say, is how much heat is absorbed by 10 grams of water if the temperature increases from 15 degrees Celsius to 25 degrees Celsius? So we could actually work this one out if you want to, but if you'd like to just discuss how to do that instead, just can anyone tell us how we would do this problem?
Is that Q equals MC delta T?
Yeah, that's just Q equals MC delta T. So the change in temperature in this case um, is 10 degrees Celsius, right? And the reason it's 10 is because 25 degrees Celsius is your T final, and 15 degrees Celsius is your T initial. And just remember that the delta T is always T final minus T initial. It's always the final temperature minus the initial temperature. So in this case, the delta T is positive, and it's 10 degrees Celsius. The mass of the problem is given, which is 10 grams of water. The specific heat, they'll only ask you to calculate heat absorbed by water. They won't ask you anything else. So the specific heat of water is in the reference table. It's one of those physical constants in reference table B. It's 4.18 joules per gram degree Kelvin. So what you would do here, let me go back to that problem. Reference table problem, excuse me. If I can find it. There we go. So you would literally plug C into that equation, 4.18 joules per gram degree Kelvin. Again, I'm not terribly interested in the answer here as well. Again, because I think you guys can obviously use a calculator, but that's one type of problem they could ask you. Another type of problem: calculate the heat absorbed when 100 grams of water are melted at 0 degrees Celsius. How'd we go about that one?
Oh, isn't that heat of fusion?
Absolutely, heat of fusion. It says melting. If it says melting, that's Q equals M times H sub F, which is the heat of fusion. And you would just plug your numbers into the equation. So we have 100 grams times the heat of fusion, which is given in that table as 334 joules per gram. That's the correct numerical setup. Again, just a calculator problem. Not obviously in this case we can figure out what it is, 33,400, because we're just moving the decimal place over 2 places. But in this case, we would need to round to 3 significant figures. And of course, the final unit would be joules, right? Since we're calculating heat. And the last question that they could ask you, that in which you could use the reference table, is to calculate the heat absorbed when 15 grams of water are vaporized. Now, in this case, it says vaporization, so we're going to use that other heat formula, which is Q equals M times H sub V. So it's basically the same formula, same form rather, as the problem above, except we're just using a different physical constant. So that's going to be 100 grams times 22,000. I'm sorry, 2,260, I believe is the number there, joules per gram. So that's, again, just another type of problem that they can ask you just based upon the reference tables alone. All right, another type of problem that they can ask you, again, where you're going to use your reference tables. And there's a good number of questions, by the way, that you just use your reference table. They can ask you to write or identify compounds. And I think you guys are pretty good at that, but I'm just going to try a couple of problems with you. The other reference table that's on that page is table F. And the types of questions that they tend to ask you with that are, which compounds are most or least soluble, things of that nature. So let me just give you a couple of examples. So First one here. What's the formula of copper 2 chromate? And I'm just going to give you a couple seconds to work that out. Copper 2 chromate. Just send me a quick done when you're done with that question. Or you could obviously verbally say we're done. Okay. Okay. Okay, so copper 2. Copper 2 obviously means that, or maybe it's not obvious, but you should know that's the charge of copper. And so you would start, whenever you write formulas of ionic compounds, you should start with the charged species first. So copper 2 has a charge of +2. Chromate is CrO4, 2 minus. And so because these ions have equal and opposite charges, you don't need to crisscross. You can simply throw them together and cross out the charges. Make sure that these compounds don't have charges at the end. And so your formula would be CuCrO4. All right, that's copper 2 chromate. Another type of problem they could ask you, how many atoms of nitrogen are there in ammonium nitrate? Thiocyanate. So again, you need to know how to write that formula before you can actually answer the question. So I'm going to give you a couple of seconds for that as well. How many atoms are there of nitrogen in ammonium thiocyanate? Just like before, send me a quick done when you're done with that as well. Okay. All right. So ammonium is a polyatomic ion, and again, it's in reference table E. So the formula is NH4 plus, and thiocyanate is also there. That's SCN minus. And just like before, because the charges are equal and opposite, you would simply cross out the charges and put two ions together, and you get NH4. Come on, SCN. Okay. Now, just to give you another example of a different type of compound, if let's say, for example, the charge of thiocyanate were 2 minus, okay? If that were the case, this formula would be different in that the ammonium would have parentheses thrown around it. You have to remember that when you crisscross, for example, if you bring that 2 down next to the ammonium, you have to put parentheses around the polyatomic ion, and that's to make sure, that's to indicate that there's more than one of them. So that would be the appropriate formula, this one here, if thiocyanate had a charge of -2. Next kind of problem they could ask you is which compound is least soluble in water. So, I mean, I don't know how you could memorize, solubility tables, although it used to be that if you took AP chemistry, you had to memorize all of table F, but they would ask you this type of question and you would have to look at reference table F. And again, reference table F is basically a solubility guideline table. Basically tells you which compounds are soluble and which are not. So in this particular case, oops, wrong page. They ask you which compound is least soluble in water. Okay, so just like before, send me a quick done when you're done with that. Okay. All right. So to answer this question, by the way, does anyone want to explain how they got their answer for this? Anyone want to volunteer? No? Okay. All right. So I'll explain it. So you're going to use reference table F for that. And just to go over this table again with you, basically there are two types of ions: ions that form soluble compounds and ions that form insoluble compounds. If you look on the left side of the table, you can see, oops, I don't want to do that, excuse me. If you look on the left side of the table, you see the group 1 ions are always soluble. So that basically means that if the compound contains a group 1 ion, you should expect that it will dissolve in water. The same is true for ammonium compounds. The same is also true for nitrate compounds and acetate compounds and hydrogen carbonate compounds and chlorates. And for most halides, that basically means that if the ionic compound contains a halide, and by that they mean chloride, bromide, or iodide, you should expect that it would be soluble in water. There are exceptions, however. Silver, lead, and mercury would be the exceptions to that rule. So as far as this question is concerned, which compound is the least soluble in water? You're looking for either a compound that contains one of the insoluble ions or one that contains a soluble ion, but what might be one of the exceptions. So I'm just going to look at the wrong answer. So, for example, sodium nitrate. Sodium nitrate is obviously not the answer because we know that nitrates, looking at the polyatomic ion table, nitrates are always soluble. We also know that ammonium sulfide is not the answer. Now, that takes a little explaining, I think. If you look on the insoluble side of the reference table, it says sulfides are insoluble. So you would expect normally that if it's a sulfide, it shouldn't dissolve in water. But there is an exception, or there are a few exceptions. The exceptions are when combined with group 1 ion or ammonium. So for example, copper 2 sulfide would be an example of an insoluble sulfide. However, if the sulfide contains a group 1 or ammonium ion, we expect that it would be soluble. So for example, sodium sulfide would be soluble, or potassium sulfide would be soluble. So ammonium sulfide is definitely not the answer. I'm going to the wrong one. Okay. Potassium hydroxide, that's also not the answer. Now, again, going back to the polyatomic ion table, if you look, it says hydroxides are normally insoluble, right? Except that there are exceptions. If combined with a group 1 ion, calcium, barium, strontium, or ammonium, we would expect that those compounds are soluble. So sodium hydroxide is also not, potassium hydroxide is also not the answer. The answer, of course, which I think you probably already knew, is lead chloride. Lead chloride is insoluble in water. Again, chlorides are normally soluble, but lead is an exception. Okay, keep going. Reference table G. I think you can probably expect what types of questions they could ask you about this reference table. Obviously, questions about solubility in 100 grams of water. Questions about which solutions are saturated or which ones are supersaturated or unsaturated, things of that nature. So I have a couple of questions based on that. So it says, which compound is least soluble in 100 grams of water at 50 degrees Celsius? So let's give that one a try. Instead of typing done, can you just give me your choice instead for this question? Tell me which choice you think it is. Least soluble. Is this one difficult?
I don't know. I'm trying to like compare each one, and
Okay.
like also they're not.
Okay. Well, okay. I got one answer. Okay, good. Everyone says A. I think for this type of question, the easiest thing to do would obviously be to go to the reference table to look at the compounds that are there. So I'm asking you for the one that's least soluble. The one thing you need to remember is that everywhere on these curves, every point on these curves represents the maximum amount of solute um, that can dissolve in 100 grams of water at a given temperature. So if you find that the maximum amount that can dissolve uh, at that under those conditions is less than another, obviously that would mean that that compound is less soluble. So basically, all you would need to do is go to 50 degrees Celsius and just go up and see which curve you hit first. And if I do that, it appears as though, and I can't tell what that is, that looks like potassium chlorate is the first curve that I would hit going up. So I would definitely say potassium chlorate, which most of you said. Okay. Okay, I guess I didn't cut this question out, and I should have, but we'll skip that one. Number 3, which solution is unsaturated? So let's give that one a try. You have 3 different solutions. Which one is unsaturated? And just like before, just give me your answer. Maybe you should do it privately, just so no one else sees your answer. Which solution is unsaturated? By the way, I hope you can't hear my landscapers. They're mowing and leaf blowing, so I hope that's not disturbing you. Okay, we got different answers. We got different answers to that one. Which one is unsaturated? Okay, I got 3 answers so far. Okay, so most of you think it's C. Okay, and I have to say I don't know what the answer is yet. I literally just made the question up, so we'll figure it out. So which one is unsaturated? So again, we're looking for the choice um, whereby the point is below the curve. I don't know if you remember that or not. Again, as I said before, every point that's on the curve would give you a saturated solution. So if it's literally on the curve like that, we would consider that saturated. And if it's below the curve, right, like down here, then we consider that unsaturated. If, on the other hand, it's above the curve, right, we would call that supersaturated. And so we need to literally go through the choices and see where the points lie. So 20 grams of sulfur dioxide at 20 degrees Celsius. So I need to go to 20 degrees Celsius. Well, if I do that for sulfur dioxide, it says that the max that can dissolve at 20 degrees Celsius is around, I don't know, about 11 or 12. So if I have 20 grams, point somewhere up here, that's a supersaturated solution. So that can't be the answer. Let's see, 30 grams of potassium chlorate at 50 degrees Celsius. So same thing. Go to the 50 degrees Celsius. So let's see, go up all the way up, potassium chlorate. Well, if I follow it all the way up to 30, the max of potassium chlorate that can dissolve is about 20 grams. So if I'm at 30, obviously that's going to be supersaturated, right? Okay, let's keep going. let's see, 25 grams of ammonia at 50 degrees Celsius. So let's see, 25 grams of ammonia at 50 degrees Celsius. So ammonia is here, that curve there. It was 50 degrees Celsius, right? So let's see, max that can dissolve is about 28 or so. So if I have 25 grams, that would give me an unsaturated solution. And did I read that right? Okay. So yeah, I would say C is the answer. Just one more thing about this particular reference table. You'll notice that basically the relationship between temperature and solubility is direct. And what that means is as temperature increases, solubility increases, but there are three curves for which that's not true, namely the ones that I'm outlining here. And can anyone, does anyone remember why the solubility is actually inverse for these compounds?
They're gases.
They're gases,
They're
absolutely.
gases.
They're gases, yeah. So you need to remember that. Gases are most soluble at low temperatures. By the way, not just low temperatures. Gases are most soluble. You really need to know that. You need to remember this. At low temperatures. What about pressure? High pressure or low pressure?
Isn't it low?
It's actually high. Okay.
Oh.
So you need to remember that. Just think like seltzer water, right? You want generally, if you want the soda to stay, more fizzy, which the fizz comes from the carbon dioxide that's dissolved in it. If you want it to stay fizzy, you keep the top on because that keeps the pressure up. That keeps the pressure higher than it would be if the top were off. So just remember that you keep your seltzer cold and with the top on because the temperature is as low as possible and the pressure is as high as possible. So that's just one of those things they could ask you on the reference table. And the last type of question that they could ask you, again, from the reference table, is how many grams of potassium chloride is soluble in 175 grams of water at 50 degrees C? So this you're not actually going to take right from the reference table, but you're going to use the reference table. And when you get your answer, just type it to me privately. I want to see if you can remember how to do this one.
Wait, Mr. Green, what was the question?
Oh, it's here.
Okay.
Number 4. Obviously, if you need to step away, you're welcome to do that. All right, so most of you have an answer, have calculated it. Again, as I said, you're not going to take your answer right from the reference table. The reason you can't do that, actually, maybe you can tell me, why can't you take your answer right from the reference table?
Because the reference table is like 100 grams H2O, and
Ex-
it's
ex-
asking.
Exactly. So because of that, we need to use or figure out on the reference table how many grams are soluble in 100 grams of water, and then set up some kind of proportion to figure out how many grams are soluble in 175. So let me just, by the way, I have to keep moving things around to see the reference table. So if it takes me a little while to do that, to remember the question. So, all right, so that says 175 grams of water at 50 degrees C. So we're talking about KCl. So 50 degrees C, go up to KCl. Let's see. KCl is, where are you? I see. So in 100 grams of water, that's about, and by the way, you're going to have to estimate, obviously. And that looks to me to be about, I don't know, maybe 42 grams of KCl at 50 degrees C. So we set up a proportion. So we would say 42 grams or 43, obviously you're going to estimate. So 42 grams of KCl over 100 grams of water. Come on. And they don't care if you label it like this, but I'm just trying to be as clear as possible. Equals X over 175 grams of water. And to get the answer, you're going to cross multiply. And I'm going to leave the units out just to be quick. So this is going to be 42, come on, times 175 divided by 100. And if you've done that and you got 73.5, then that would be the answer. And since I didn't actually calculate this, but I'll do it right now, 42, oops, come on, times 175. So yes, 73.5 would be an acceptable answer. So now I can continue going through the reference table types of questions as I've been doing. If any of you would like me to go over a particular question or type of question in general, I can do that as well. Does anybody have any suggestions, or would you just like to continue going over the reference table types of questions? I have other questions prepared as well, but anything in particular that's pressing?
No.
No? Okay. All right, so let's continue. So reference table H. Reference table H is a vapor pressure for liquids table. There are a few different types of questions, not really many, that they could ask you based on this. They could obviously ask you for the vapor pressure of different liquids at different temperatures. So they might say something like, what's the vapor pressure of water at 20 degrees Celsius, which you would just pull it off the curve. Hopefully you get a question like that, because that's real easy. But more than likely, you're going to get questions like this. The first one is what I just said, right? What's the vapor pressure of ethanoic acid at 30 degrees Celsius? Again, you just pull that right off the reference table. I'm going to trust that you can do that, so I'm not going to ask you to do this one. But this one here, which liquid has the weakest intermolecular forces of attraction? So just like before, private message me your answer. Which one has the weakest intermolecular force of attraction? Okay, I got one answer. Okay, two answers. Or one answer, rather. Is this one difficult? I see one answer so far. Weakest intermolecular force of attraction. I see one answer. Okay. I see two answers. Okay, so far I only see two answers. I don't know why that type of problem would give you that much difficulty. By the way, if you see a question like strongest or weakest or biggest or smallest, those types of extreme type questions, obviously what you can do is you can eliminate the ones that are in the middle. And so if I look at reference table H, there are two liquids that are sort of in the middle of the group. Ethanol and water are in the middle, so we can probably eliminate those. And So how do you figure this out? Anybody want to explain how they got their answer? Propanone, for example. Somebody had propanone.
I said propanone. I had propanone. Jesse
Okay.
said.
Okay.
I had propanone because like it just the vapor pressure and like the temperature was the lowest.
Okay.
And
Okay, so let's just go back. This type of question. So vapor pressure, what is that caused by? It's caused by molecules leaving the liquid phase and entering the gaseous phase. Those molecules, they exert what's called vapor pressure. Vapor is just another word for gas. And why would a liquid have vapor pressure? Well, because the liquid's evaporating. And so if it's a closed container, for example, those evaporating molecules, they're creating pressure against the side, or they're exerting pressure against the sides of a container. So the key about vapor pressure is that the molecules have to be in the vapor phase. Now, if they're not in the vapor phase, then they're not exerting vapor pressure. And why might they not be in the vapor phase? Well, if the molecules are really strongly attracted to each other in the liquid phase, if they have strong intermolecular forces in the liquid phase, then you're not going to have many molecules in the gaseous phase. They're going to stay down here as a liquid. And so if you're ever asked the question, which liquid has the highest, the weakest intermolecular force of attraction, it's going to be the one that has the highest vapor pressure, because if the molecules are not attracted to each other down here in the liquid phase, they're going to be a lot of them up here in the vapor phase. So the liquid with the weakest intermolecular force of attraction would be the one that has the highest vapor pressure at any temperature. So if I just start at, let's say, 50 degrees Celsius, right, and I go all the way up, clearly I can see that propanone has the highest vapor pressure of any of the liquids in table H. So that would be the answer. Obviously, they could flip it around. They could say which liquid has the strongest intermolecular force of attraction, in which case the answer would be ethanoic acid. But just be aware of those types of questions. I seem to have seen those types of questions a lot of times, actually. All right, let's keep going. Okay, other type of question they could ask you based on reference table H, what's the normal boiling point of ethanol? So again, they're not expecting you to memorize boiling points of compounds. And so you would use, for something like that, you would use reference table H. And so, just like before, private message me your answer. Aoife, you still there?
Yeah.
Okay. Normal boiling point. Okay. Okay, I have two different answers. Okay. All right, so I don't know if you, maybe, I see, good. Okay, so just be careful, because ethanol and ethanoic acid are obviously different. And so I think maybe some of you confuse the two. So, okay, so how do we figure this out? What you need to know is the normal boiling point of any liquid is the temperature at which the vapor pressure of that liquid equals the atmospheric pressure. So if they're asking for the normal boiling point, basically they're asking you at what temperature is the vapor pressure of that liquid equal to 101.3 kPa. So basically everywhere these curves intersect the 101.3 kPa line, which is standard pressure, that's the normal boiling point of that liquid. So if I want to know the boiling point of propanone rather, I just drop a vertical down, and that's about 55 degrees Celsius is the boiling point of propanone. If I want to know the boiling point of ethanol, which is right here, right, that's about, if I drop that all the way down, that's probably about 79 or 80, it looks like to me. Ethanoic acid is way over here. And that could be 117, which is what I got from some of you. but that's ethanoic acid. So just be aware, just be very careful. Ethanoic acid and ethanol are obviously different compounds. Ethanol is an alcohol. Ethanoic acid is an organic acid, right? We know that because it ends in OIC. Now, notice that I said here normal boiling point, right? The normal boiling point is the temperature at which the liquid will boil under normal, so-called normal conditions or standard conditions. Most of the times that's 101.3 kPa, but we know that if the standard pressure or the pressure above the liquid is not 101.3 kPa, well then the boiling point is going to be different. Like I think we discussed the fact that at higher elevations, the air pressure is less than it is at sea level. So let's say down here, where you are, today's pressure might be 101.3 kPa, more or less, but at a higher elevation, let's say Denver, Colorado, it might be like 98 kPa. And so because of that, the boiling point of those four liquids that you saw will be different than it is down at sea level. So if I ask you, for example, what's the boiling point of water when the applied pressure is 50 kPa? How do you figure that out? Again, private message me your answer. What's the boiling point of water when the applied pressure is 50 kPa? Okay, I see an answer. Okay, I see, wow, I see a really different answer. Okay, I see two similar answers.
Mr. Green, can you show the question again?
Oh, okay, I'm sorry. So the
show-
question is, what's the boiling point of water when the applied pressure, that's like the air pressure, when it's 50 kPa? Boiling point of water when the applied pressure is 50 kPa. You still, okay, good. Well, see, now it's interesting. The numbers are really different from each other. So how do you do this? So I told you that if you want to know what the normal boiling point is of a liquid, that would be the temperature at which the vapor pressure is equal to 101.3 kPa. So basically, everywhere the curves intersect this 101.3 kPa line, just drop a vertical down, and that would give you your boiling point. But if the applied pressure is not 101.3 kPa, if it's, for example, 50 kPa, you have to basically do the same thing. You can draw a line all the way across the curves in table H, and just like you did before, just drop a vertical down for where the vapor pressure equals that pressure, which in this case would be 50 kPa. If I drop a vertical down from here, what do I get? I'm going to have to estimate that, but let's see. That looks to me about, I don't know. Do I have the right curve there? Let's see. That's definitely 50 kPa. That's 75. That's 80. All right, about 82, 83-ish, something like that. Does everybody understand that? Because nobody, or one person, actually, let me see. How many people wrote that? Only about one person wrote about 82. Is that clear? Is there anything that's unclear about that?
Yeah, I did a proportion, which
Yeah.
I realized is wrong.
Okay, yeah. You're not going to ever have to do proportions if they ask you for the boiling point. Basically, all you're going to do if they ever ask you about boiling points of these liquids, that you simply have to, again, as I said before, just look at where the vapor pressures equal the pressure that's given in the problem and drop a vertical down from that temperature. Now, they can On the other hand, they could ask you about the boiling points of elements. Like, for example, they could ask you, what's the boiling point of, I don't know, iron, for example, or what's the boiling point of hydrogen gas? If they do, that's really easy because all you're going to do is you're going to go to reference table S, I believe it's what that is, reference table F, and you can see the boiling points and melting points of every element, or virtually every element in the periodic table. So that's not even something you would need to look at reference table H for. You can just pull it off table S. Let's continue with reference table questions. Again, if you have any other questions outside of this, you can stop me at any point. So we're on reference tables I and J. And so reference table I is a table of heats of reactions. Obviously, they could ask you questions like, which reaction is endothermic, which one is exothermic. Those are real easy because if you look here at the bottom, it says if the minus sign is indicated in the heat of the reaction, that means it's an exothermic reaction. So for example, the first reaction here is exothermic because the delta H, the enthalpy of the reaction, is negative. Just something else to be aware of with this type of information. It says here that the delta H is negative. It says negative 890.4 kilojoules. Sometimes they'll put the heat, this heat value, they'll put it in the equation. So this heat of reaction is 890.4 kilojoules. And so what they could do is they could put it in the reaction, but they'll put it on the product side. So they'll say, they'll give you this reaction and they'll give you plus 890.4 kilojoules. Now it does say positive here, right? But please understand that because the heat's on the right side of the equation, that means it's an exothermic reaction. Okay, so they could ask you stuff about that. Next to that is reference table J. This is an activity table. I have some questions for you based upon that. But these types of questions that they ask you, they tend to be pretty easy. And I'm just going to show you a couple of examples of that. So, for example, this one here, which metal will react with hydrochloric acid to produce H2? So, give that one a try. And private message me your answer. Which of the following metals will react with hydrochloric acid to produce H2, hydrogen gas? I see one answer, good, and it's the correct answer. Okay, I see another answer, good, that's the correct answer. Okay, I see good. Okay, I'm just going to wait for one more answer. Oops. Okay, so I got most of your answers. Okay, so you need to remember there's a certain property of acids, and that is they react with certain metals to produce hydrogen gas. I suspect at one point this was a very useful technique for scientists to be able to produce hydrogen gas, and so that's why it seems to make its way into the curriculum and textbooks and things like that. But so how do you figure out this answer? Well, you're going to look at the activity table, and actually, before I do that, let me just go back to the question. What you need to know here is that when metals react with HCl to produce hydrogen gas, what's really happening here is it's a single replacement reaction. So it looks something like this: X plus HCl, come on, to produce H2. and then some other kind of metal halide like that, XCl, something like that. Depending on what these metals are, you would balance it one way or the other. So it's a single replacement reaction. What's happening here is the metal would be replacing hydrogen. That's what has to happen in order for that metal to react with hydrochloric acid to produce H2. So how do you figure out which ones will do that? Well, any metal or any element can replace another element if it's more active than that element. So in order for the element to be able to replace hydrogen, it would have to be more active. So if you look in reference table J, hydrogen is down here. It's not very active at all. It's obviously not a metal, but they put it here for reasons that I won't get into right now. But so in other words, in order to replace hydrogen, that metal would have to be above hydrogen. And so the only one that fits that bill, because copper, silver, and gold are not as active as hydrogen, the only one that fits that bill would be iron. So iron will react with acids to produce hydrogen gas. And I've seen that question a few times on the Regents. Actually, a lot of times. All right. Number 2, in the following redox reaction, which metal would act as a cathode and an associated voltaic cell? So you're supposed to be able to figure out what this voltaic cell would look like just from a reaction. So give that one a try. And again, private message me your answer. Okay. So I have one answer. Oh, I got 2 answers. I'll just wait a couple seconds more. Okay. So we're divided on this answer, apparently. All right. So I really hope that you guys don't get a question like this wrong. This is as easy as A, B, C. So if they ever ask you which metal is the cathode, one thing you need to remember is that, first of all, a voltaic cell is a spontaneous electrochemical cell, which means that electrons are flowing spontaneously in a particular direction. I would use table J for this. What you need to know is that electrons always flow spontaneously down table J, right? So for example, if I look at the problem that I had here, I had aluminum and zinc, I believe, right? So it's either going to be aluminum or zinc. So we go to table J and we find aluminum, and let's see, aluminum is here and zinc is down there. So aluminum is more active than zinc. So that means that spontaneously electrons will flow from aluminum to the zinc. So you need to remember something here. So the element that's on top of table J, that's always going to be your anode. Always. In fact, one way you can remember it, anode is the one that's most active. AA. Okay? And of course, anything that's below the anode would have to be your cathode. So electrons are going to flow from aluminum to zinc in this case. Zinc would be your cathode. Right? So cathodes are always lower on table J. Anodes are always your most active metals. And so if you were to envision a voltaic cell using these metals, what you would have is you would have something like this. You'd have 2 half cells, right? And then something like that. And then you'd have your salt bridge, which is very sloppy, but I think you get the picture. Then you'd have your voltmeter, right? And then one of these would be zinc. Come on. And one would be aluminum. And again, because zinc is, again, according to table J, come on, find it again. According to table J, zinc is less active than aluminum. Electrons are going to flow from aluminum to zinc. So in your diagram, you would expect electrons to flow that way, right? Because zinc is your cathode. Remember, electrons always flow toward the cathode. Always, always, always. Electrons always flow toward the cathode. and away from the anode. Another question they could ask you, and I'm just jumping around because I have a lot of different questions they could ask you about voltaic cells. They could ask you what's happening at that electrode, at the cathode. What's happening to the mass? You need to remember that at the cathode, it always gains mass. It always gets fatter. Just remember fat cat, the cathode always gets fatter. The anode always gets smaller, so it loses mass. They could ask you the purpose of the salt bridge. What's the purpose of that? Why is that there? Anybody?
It permits the flow of ions.
There we go. Exactly. That's literally what I want you to write. It permits the flow of ions. Don't say anything different. I don't want anyone to possibly, misinterpret what you mean with that. All right. Another question, again, based on those two reference tables, and this is a little bit less intuitive. How many joules of energy would be produced by the combustion of 2 moles of propane? Now, that's one of those questions like, how would we know that? How would we possibly know that? And if you ever come across questions like that, like, how am I supposed to know that? 9 times out of 10, it's a reference table question. So looking at reference table I, you see that there's a combustion reaction there. And in particular, there's a few different combustion reactions. In fact, there are 1, 2, 3, 4, 5, 6 combustion reactions. But you're only interested in propane, and propane is this one right here. Right? So if they ask you how many joules of energy would be produced by the combustion of 2 moles of propane. 2 moles. Right? What would you say? And again, inbox me your private message me your answer. 2 moles of propane. Okay, I see 1 answer. I see 2 answers. I see, okay, so everybody's interesting. And I actually made this question more difficult than I was intending to, and for a reason that may not be obvious to you. And I think it wasn't obvious to you, but so obviously we know we can use this equation here. And this equation clearly says that for every 1 mole of propane, you're going to get that much heat. So what a lot of you did, and I can understand why you did that, you multiplied the number here by 2, because if 1 mole will get you this much heat, well, obviously 2 moles will get you twice as much. And the reason I made this problem more difficult than it needed to be is because this is given in kilojoules. And so the answer that you typed is actually in kilojoules. You would need to multiply your final answer by 1,000 in order to get that in joules. But more than likely, what they would ask for this type of question, they would ask you how many kilojoules. They probably wouldn't make it doubly difficult by asking you to convert it to joules. In fact, I've never seen a question like that where they asked you to convert it, calculate an answer, and then also convert it to joules. So I think they would probably have accepted your answer if you had left it like that. All right, so we're on tables K and N, or table KL and N. There's a lot of different questions they can ask you about these reference tables. And I have a few of these for you here. So which of the following is an Arrhenius acid? Again, private message me your choice. Okay, we got different answers. Okay. Okay. All right. Well, hopefully you saw. Hopefully you see the answer is in fact choice A. In order to be an Arrhenius acid, you need to remember that Arrhenius acids are substances that produce H plus ions as the only positive ion in solution. And so in order to be an Arrhenius acid, it has to have hydrogen at a minimum. And so choice C obviously can't be the answer. Neither can choice choice D be the answer because those compounds don't have hydrogen. The only Arrhenius acids that they will most likely ever ask you about are the ones that are in table K. So in most cases, if they ask you which compound is an Arrhenius acid, it's going to be one of these. It's
Wait,
really
so
Go ahead, I'm sorry.
so on table K, those all aren't Arrhenius acids though, because CO2 is there.
Ah, okay, very
Yeah.
good. I see, I see. You know what? Yeah, I made okay. What you Yeah, that's really nasty for me to have included that. I actually didn't look at this table before I typed that up. Yeah, CO2 is not an Arrhenius acid because it again, an Arrhenius acid is a substance that when you put it in water, so if I have a general acid like HA, this is just a general way of writing an acid. If you put it in water, part of it will break off. The H plus will break off like that, and you'll be left with another negative ion, whatever is in the particular compound. So, for example, if this is HCl, which is an example of an Arrhenius acid, if you put it in water, it's going to ionize into H plus and Cl minus. Now, carbon dioxide can't do that because it doesn't have hydrogen. Now, what the reason they put that there is because carbon dioxide, when you put it in water, it will acidify the water. It does produce something called carbonic acid, and carbonic acid H2CO3, which by the way is unstable and it literally decomposes into CO2 and H2O. But this is an Arrhenius acid because it has hydrogen. So yeah, they wouldn't put carbon dioxide as a choice because that's confusing, right? But you need to know that Arrhenius acids have to have hydrogen in order to be considered as such an Arrhenius acid. So yeah, HBr would in fact be your answer. NH3 obviously has hydrogen, but this is not an Arrhenius acid because when you put NH3 in water, it will not produce H plus in water. In fact, it's a base. If you look at reference table L, you'll see that it's actually there as a common base. So more than likely, if they ever ask you for which one is an Arrhenius acid, it's probably going to be one that's in the reference table. So you can just, in most cases, look it up. This question here, what's the color of bromocresol green at a pH of 7? So let's give that one a try. What color is bromocresol green at a pH of 7? Okay, we got 3 answers. Blue, okay. Everybody thinks it's blue. Okay, so let's see if that's true. So again, you're not expected to memorize the color conventions of indicators. So bromocresol green here, it says at a pH of 3.8 and lower, right? 3.8 and lower, it would be expected to be yellow. At a pH of 4.5 and higher, it would expect to be blue. By the way, if the pH range is in the middle of those, you'd expect it to be somewhere between yellow and blue, perhaps green. And since the question said pH 7, that's definitely above 5.4. So yeah, this would definitely be blue. Those types of questions I think are pretty easy, but if you don't know where to look, obviously you can get it wrong. These questions here I'm worried about. Write the nuclear decay equation for cesium-137. I'm afraid that you guys aren't going to remember what to do with that. So let's give that one a try. Write the nuclear decay equation for cesium-137. And there's obviously no way to inbox me your answer, but just let me know when you're done. Okay, so it looks like most of you are done. Hopefully you knew that in order to answer this question, you need to go to reference table N and look up cesium-137. And cesium-137, according to reference table N, is a beta emitter. So that means it's going to give off a beta particle. And hopefully you know that a beta particle is basically an electron. And so to write this equation, you would start out with a nucleate symbol for cesium-137. So to do that, I need to find, first of all, what the atomic number of cesium is. And you need reference the reference table for that, or the periodic table. Let's see that the atomic number is 55. And so going back to the equation, to the problem, it says cesium-137, oops, and then 55. Come on. And it gives off a beta particle. So that's going to look like that. Hopefully you know that that's a product, right? It says beta mode, or the mode of decay is beta. That means it's going to give off a beta particle. That means it's going to produce a beta particle. And then, of course, another particle is going to be left. And so to figure out what the atomic number is of that compound, or that element is, you would have to ask yourself, what atomic number do I add to -1 to get back 55? Of course, that's 56. Right? And then you say, what mass number do I need to add to 0 to get 137? Of course, that's 137. And then the last thing I need to do is to figure out what the element is of an atomic number of 56. So I go back to the periodic table of elements, find that. Let's see, atomic number 56, that's barium. So this would be the transmutation of cesium-137 to barium-137. And by the way, this is transmutation. The reason it's transmutation is because you have one element changing into another via radioactive decay. And this is also what we call natural transmutation. Why is this natural transmutation?
Because there's only one reactant.
Exactly, one reactant. And the other thing you need to remember about nuclear decay equations is that the reason that this species undergoes radioactive decay is because it's considered unstable. Unstable, okay? The nucleus tends to fall apart to form something else. Now, there are certain elements that are just naturally radioactive, even though they're not in table N. Do you remember which ones are? Do you remember which elements are naturally radioactive? I got crickets for that one. Okay. All right. So I'm glad I asked that question. Elements that have atomic numbers greater than 83 are naturally radioactive. So anything atomic number 84 and higher is naturally radioactive. So starting with polonium. Polonium is actually radioactive. Astatine, radon, and anything higher than that is naturally radioactive. So the smallest how do I say this? The smallest element that's not naturally radioactive is bismuth, right? So it has atomic number of 83, but anything higher than that is naturally radioactive. Okay, I have seen questions like that before. All right, let's keep going.
Wait, can you go over like the radioisotopes and like their functions, like those ones that we have to memorize?
Yep, absolutely. There's about 5 you need to memorize. Okay, so which ones are they? The one that they ask you not every year, but I see it all the time, iodine-131. That's for treating thyroid disorders or thyroid cancers. They may phrase it as, treating thyroid disorders, or they may phrase it as treating thyroid cancer or diagnosing thyroid disorders, things like that. Bottom line, iodine-131 has to do with thyroid. They'll never ask you anything other than that as far as iodine-131 is concerned. Carbon-14 is used for dating. But the key here is that the things that they're dating, they have to have once been living, material. So anything made of paper, anything made of wood, animal skins, things like that, something that was derived from something that was once living. They use it to date those types of materials. Another one they tend to ask you is cobalt 60. Cobalt 60 is for treating cancer. For treating cancer. They'll just say, cancer. They won't specify, what type of cancer, but they'll just say, treating cancer. Uranium 238 is used for dating as well, but it's used for dating things that are non-living and things that have that are older than 50,000 years. Let's say carbon-14 is only good for dating things that may be only about 50,000 years old. But if you have something that's older, you need a different radioisotope. And so the one that they show you a lot is uranium-238. That's used for dating things like rock formations, things that are older than 50,000 years old. And what else? What else? I'm thinking there's one more. I'm thinking it's technetium 99. Technetium 99. That's used for imaging, diagnostic imaging. So things like, for example, if you have a heart condition and doctors want to image the blood vessels in your heart or want to image the blood supply in your heart, they use technetium 99. They inject you with technetium 99, and then they look at your heart using some sort of imaging device. They can see what the heart looks like, what the blood supply looks like, what the how the heart is pumping using this device. And those are the only ones that you probably won't see technetium 99 though. I'll be honest with you, but the ones you see over and over again are the ones that I just mentioned to you before. Okay, and it's been a while for half-lives, right? So I'm going to ask you to do this one. I might ask you to do more than just this one because I'm worried about half-lives. I don't know if you guys remember that too much. So this one here, number 4. I'm sorry, Haley, did I answer your question?
Yeah.
Okay. All right. So how long would it take for 100 grams of potassium-42 to decay to 12.5 grams? Let's give that one a try. How long would it take 100 grams of potassium-42 to decay 12.5 grams? Inbox me your answer privately, please. By the way, I don't want to scare you, but I don't think I'm even halfway through this review. So if you guys want to take a break, let me know. But if you don't stop me, we'll be here for 3 hours plus.
Phew.
It's too bad there's not more people here. It's really too bad. All right, so everybody says 38, around 37 hours. At least, let's see, how many people that? 1, 2. Okay. All right. I guess I'll go over that. So hopefully you realized that to go from 100 grams to 12.5 grams, the sample is going to have to be cut in half a certain number of times, right? So the easiest thing that I would do for this is I would literally count how many times a sample has to be cut in half to get there. So first thing it's going to do is cut in half to 50 grams after one half-life. After another half-life, I'm going to have 25 grams. After another half-life, I have 12.5 grams. So this gives me, come on, 12.5. So this gives me 3 half-lives. So if I go to reference table so-and-so, reference table N, and what was that, cesium-137? Nope, come on. Potassium-42, okay. So potassium-42, it says the half-life of potassium-42 is 12.36 hours. So since we know that that's 4 half-lives, we would multiply 12.36 by 4. And that looks like it's going to give me what most of you, oh no, I'm sorry, not 4, excuse me, 3.
By 3, right?
Yeah, it's 3 half-lives. I wrote 4. I can see 3 arrows there. Obviously, it is definitely 3 half-lives. So yes, that will give me what you guys typed into the inbox. Okay. All right, so we're almost there. So we're on reference table O and P. So there's a bunch of problems they could ask you about that. We did a few problems using reference table O or table P and Q. Those are organic chemistry types of questions. I have to admit I do worry about those as well. We haven't done organic in quite some time. And but the good thing about organic, guys, is that they don't really expect you to memorize a whole bunch because a lot of the information is actually in the reference table. So I want to give you a couple of examples of that. So number 1, which of the following compounds is a saturated hydrocarbon? I see one answer, and it's the correct answer. Oh, see? Okay, good. Okay. I don't know if Leah's still with us. I see her there. Okay. All right. So first of all, saturated. What you need to know about that, saturated basically means, you guys tell me.
It has single bonds.
Single bonds, exactly. And if it contains single bonds, that means it's an alkane, right? Alkanes contain single carbon-carbon bonds. If you forget that, as I said before, it's in the reference table. If I go look at reference table Q, I see that the alkane series contains, again, single carbon-carbon bonds. If it's an alkene, it contains a double carbon-carbon bond. And if it contains a triple bond, it's what we call an alkyne. And so you have to figure out, based on the formula, which one is a saturated hydrocarbon. And so since we know it's an alkane, because we know that alkanes contain only single bonds, we know the general formula has to conform, or I should say the formula has to conform to this general formula, CnH2n plus 2, which basically means the number of hydrogens is twice the number of carbons plus 2 more. And so if we go back to that problem, the only one that conforms to that would in fact be choice C. Because in this case, the N here is 6. The number of carbons is 6. And if I go 2N plus 2, where N is 6, obviously that's going to give me 14. And so my formula would be 6C6H14, which, by the way, would be what alkane? What is that, C6H4? Assuming it's a straight chained alkane.
Hexane.
Hexane, definitely hexane. All right. Identify the functional group in butanone. It's difficult to inbox that to me. So just when you're done, let me know. Functional group. Just let me know when you're done. Okay, so as far as functional groups are concerned, again, they don't expect you to memorize what the functional groups are, but you do have reference table R, and it does tell you what the functional groups are. So the only thing you need to do with this problem is to identify what type of compound it is. And since it says butanone, the ending here is ONE, and all compounds that end in ONE, if I look at the examples, has to be a ketone. And so the functional group, if they ever ask you for what that is, you would just do that, because if you look at the table, it tells you what the functional groups are. So if they ask you the functional group of a ketone, you would just literally write what they gave you. Just a couple of things about some of these compounds, they often won't give you the complete structural formula. They may give you the condensed structural formula. And so for ketones, for example, what you might see is you might see something like this, CH3CO, 2H3. You just have to know that that CO in the middle of a compound is a carbonyl group, like that. You're expected to know that. Likewise, they may give you an aldehyde, but again, they'll give you the condensed structural formula. For example, they may give you something like this, CH3CHO, like that. You're expected to know that if it's got a CHO, it's an aldehyde. It's got the functional group, this one here, C doubly bonded to an O bonded to an H. It's just one of those things you're just going to have to just be aware of. Again, they don't expect you to memorize it, but just make sure you look at reference table R if there's any doubts about what type of compound it is. Let's keep going. Let's see, where am I? Okay. Which of the following is an organic acid?
Wait, if they ask you for the functional group,
Mm-hmm.
would you actually have to draw out the structure and not just write CO?
You know what? I think they'll take both, but just to be on the safe side, if they ask you for the functional group, I would give them what they're giving me. In other words, in the reference table, it clearly says the functional group is what you just saw. So that you cannot be marked wrong if you're just spitting back what they gave you in the reference table. Again, if I'm sitting there and I'm grading it, I see CO, I'm going to give that credit. But just to be on the safe side, you just don't know how the person grading your paper will take it. I would just give them exactly what's there in the reference table, just so that there's no possible way they can mark it wrong. That's a good question, by the way.
Okay.
Which of the following is an organic acid? Okay, most of you just jumped on that really quickly. And again, you're not expected to remember what the functional groups are, but if you see a COOH like that, that's an organic acid. This one I just finished telling you before, CHO, that's an aldehyde. This one here, what's that?
Alcohol?
That's definitely an alcohol. And I'm going to keep saying this until I'm blue in the face. They will sometimes throw this at you and ask you if it's a base. And you're likely to say that it is because you see OH. Remember, Arrhenius bases contain OH, but this is not hydroxide. This is what we call hydroxyl, right? This compound looks like this, like that. And so that is not a base. It's also not an electrolyte. Sometimes they do that. They'll say, which compound is an electrolyte? And you see that compound and you think, okay, it's a base, so it's an electrolyte. Again, it's not a base, it's an alcohol. There are only 3 things that are electrolytes in water: acids, bases, and salts, not alcohols. Alcohols are not electrolytes. Let's keep going.
Wait, Mr. Green?
Yes.
Table O?
Table O, okay.
Yeah. Can you just, sorry, this is kind of like off topic. Can
Okay.
you just, which has the greatest penetrating power and like that?
Oh, yes. That's
I was-
fantastic. Thank you. That is a fantastic question. I don't know why I didn't remember that question. That's a really, really, really good question. It actually spins off another question in mind too. If I can find table O, where is it? There it is. Okay. All right. Greatest penetrating power, real easy. If you know your ABCs, you can memorize this. Real simple. Alpha, beta, gamma. That's like ABC. And so in terms of penetrating power, it goes from least to greatest, alpha, beta, gamma. Alpha has the least penetrating power, beta has the second greatest penetrating power, and gamma has the greatest penetrating power. So ABC, alpha, beta, gamma. That's really not a C, it's probably a G, but just alpha, beta, gamma, that's the order. The other thing.
And then mass is opposite.
Yeah, exactly. Excellent. That's exactly right. Gamma is not a particle. This is electromagnetic radiation. It's energy. It has no mass nor charge. Beta particles also have no mass. The masses are here, by the way. You can see them in Table O. And alpha particles have a mass of 4 mu. The other thing they could ask you, and this is I've seen this in a number of different Regents questions. They'll give you this type of diagram, which you probably already know what I'm gonna, but even before I finish it, um, they give you this type of thing where you see 3 different trajectories like that, and you have to identify which one is which, like that. So the one that curves down, which one is that?
Beta positive.
Okay, well, they'll ask it this way. They'll say, is it alpha, beta negative, or gamma? That's what they'll say.
Alpha.
Alpha.
It's definitely alpha, right? And the reason that it's alpha, the other thing you need to remember is that alpha particles are positively charged. Alpha particles are positively charged. That's what's not given in Table O, unfortunately. And the reason for that is because an alpha particle is really just a helium nucleus. It's a helium nucleus. And by that, I mean it's got no electrons, right? So a helium nucleus has 2 protons and then 2 neutrons, right? And remember, neutrons have no charge and protons have positive charges. So a helium, an alpha particle it's really a helium 2 plus ion. That's really what it is. And so unfortunately they don't tell you that, but so that thing that goes down is definitely an alpha particle. The one that goes up is
Wait, Mr. Green.
Yes.
Couldn't it be a positron though? Since
Yeah.
the positron.
Yeah. They could obviously, you could assume it's a positron as well. But in years past, I've never seen that as an option. Obviously, it could be, but I've never seen them throw that in. But I'm glad you realize that any kind of positively charged particle, you would expect that it would be deflected by the positive plate. But again, I've never seen that as an option. But obviously, it could be. First time for everything. Okay, so let's keep going with that. So we're on reference table. What reference table was I on? So I was on reference table R. Okay. So that's pretty much an overview of the reference table. I mean, obviously you have your periodic table, which is a bunch of stuff you could get from this. Hopefully you know that you can get the electron configuration from the periodic table. You can also get from the periodic table how many shells or energy levels the atom contains. So for example, if I ask you for the electron configuration of magnesium, you would just look that up. By the way, SPDF is not on the reference and not on the region, so you're not going to have to say 1s2, 2s2, 2p6 if they ask you. And by the way, if you do, that's okay. I would almost rather you not do that, only because there's a chance you could get it. You could just not remember it properly. But if they ask you for the electron configuration of magnesium, for example, you're just going to say 2-8-2. The other thing you can get from the periodic table is a number of valence electrons. Hopefully you remember the number of valence electrons are given by the last number. So magnesium has 2 valence electrons. Every element in group 2, in fact, has 2 valence electrons. That's always true. Elements that are in the same group have the same number of valence electrons, and that's why they have similar reactivity. If they ever ask you, why do these elements react similarly? The answer is going to almost always be because they have the same number of valence electrons. The other thing you can get from the periodic table is Lewis dot structures. So for example, if they ask you for the Lewis dot structure of, let's say, carbon, right? Remember, Lewis dot structures contain valence electrons only, so the electron configuration of carbon is 2-4. So you're going to put 4 dots around the chemical symbol for carbon. You can do it that way. Just remember, for Lewis dot structures, don't put more than two dots in any one spot. You can put them anywhere as long as you don't put more than 2. And basically, this, I shouldn't say you can put them anywhere. I should say you can only put them in 4 spots, right? 12, 6, 3, and 9. But other than that, as long as you don't put more than 2 in any one spot, and you only put them in those 4 spots, you can have a lot of different patterns for electron dot structures. Obviously, you can get the atomic mass from the periodic table. If they ask you for the molar mass, of the compound, you're going to use the atomic masses that are here. It's okay if you round the atomic masses to the nearest tenth. In fact, sometimes they say that in the question. It's also okay, by the way, if you round the atomic masses to the nearest integer. That's actually okay. They will accept that, but oftentimes they ask you to round to the nearest 10th. What else? What else can you get from the periodic table? Charges, possible charges when the element forms compounds. So you should remember that group 1 and group 2 elements always have +1 and +2 charges. You have these elements in the center, transition elements. They have multiple oxidation numbers, multiple charges. So if you have to name a compound with a transition element, make sure that you indicate what the charge is with a Roman numeral if there's more than one. What else can you get from the periodic table? They could ask you things like, for example, the valence electrons in vanadium. The valence electrons in vanadium are in which energy level? They could ask you that. So vanadium, for example, is in period 4, right? So that means it has 4 shells. So if they ask you what energy level the valence electrons are in, you're going to say energy level 4, or n is equal to 4. There's a number of different questions they could ask you from the reference table. There are trends that I gave you guys to memorize as far as trends in atomic radius, ionization energy, electronegativity. You're welcome to try to memorize those, but frankly, you have 3 hours to take this exam. And so all the trends that we discussed, they're literally all here in reference table S. You don't need to memorize any of them. Electronegativity is here. Ionization energy is here. Atomic radius is also here. You don't need to memorize anything. The one thing that's not here is the trend in ionic radius. And for that, you need to know that the trend in ionic radius is exactly the same as the trend in atomic radius. So basically, what does that mean? That means that generally speaking, go back, ionic radius increases going down and decreases going across. Okay? So that's pretty much it as far as the reference tables are concerned. Okay. And that's pretty much it as far as reference tables in general. I have a bunch of other questions here that are based on an actual Regents exam.
Wait, Mr. Green, I have a question. Yeah. When NaOH dissolves in water, does it yield hydroxide or hydronium?
Okay, so NaOH is a base. First of all, it contains hydroxide. So when it dissolves in water, it's going to do the only thing that it can do. It's going to dissociate. It's going to break apart into Na plus and OH minus. All compounds that contain OH, and by that I mean it contains OH bonded to a metal atom, right? That's the key. It has to be a metal atom. Are bases. And if they're bases, when you put them in water, they're going to dissociate into some kind of positive ion, always the metal atom, and then hydroxide. So that's definitely what we call an arrhenius base, and it's going to produce hydroxide solution.
Then what produces hydronium?
Hydronium are acids. Now, again,
okay.
Remember, acids, arrhenius acids, when you put them in water, they ionize to form H plus, and Cl minus. But you need to remember that water has these lone pairs of electrons. And so when water encounters the H plus ions that are in solution, it literally forms a bond with it. It forms a coordinate covalent bond. And so what you get instead in acid solutions, you don't actually have any H plus. Let me be clear. In acidic solutions, you actually do not have any H plus in that solution. It's all in the form of what we call hydronium, or H3O plus. But you're expected to know that arrhenius acids produce H plus in solution, right? But just understand that in acidic solutions, really that H plus is going to be in the form of hydronium, not H plus. Okay. All right. And hydronium, by the way, is in table E. It's a polyatomic ion. So if you ever forget what that is, it's an H3O plus. H3O plus is the actual charge. Okay. Now, before I get into Regents questions, are there any sort of like, questions that stand out in your mind? Like, I feel like I don't really understand that. Can we go over it? Anything? Just throw out.
I have like a general question
Okay.
about the packet you gave us on the last day of school.
Yep.
Oh yeah.
That was really hard, Mr. Green.
Yeah. As I said before, I literally chose the most difficult questions that I could possibly find.
Oh no, nobody. Yeah, no, you did say that, so I was kind of freaking out.
Yeah, I'm just trying to give you as best a shot as I can possibly provide. I don't think you'll see questions that are more difficult than those. I actually have that packet here. I didn't load it into Active Inspire. I can do some of those questions if you want.
Can you post the answers?
Yeah, I can do that. I
haven't finished it, so I don't want to
Yeah, I can do that. I can certainly do that. By the way, obviously be better to be, face to face for a type of review like this, but I think this is definitely a close second probably to being face to face. What I plan on doing, since I think for the most part that this review, I think it did serve some purpose. What I plan on doing is the night before the exam, I can do another one of these, and I'd like to have as many people as possible. So
Yeah.
I can also answer those questions there as well. But I can post the answers, obviously. That's not a problem at all. So anything else?
Wait, yeah. For the heat, the average kinetic energy and potential energy.
Yep.
I don't know when they decrease and remain the same.
Okay. All right. So you're talking about a heating curve.
Yeah.
All right. So this is what a heating curve is. So here's what you need to know. Basically, potential energy, this is really easy to remember. Potential energy always increases going in that direction. So in other words, if the sample is being heated, if it's a heating curve, potential energy always increases everywhere. So whether we're talking about going from here to here, let's just call this from A to B, that potential energy increases. If we're going from B to C, potential energy increases. If we're going from C to D, potential energy increases. D to E, right? So everywhere on this heating curve, it always increases. Now, if we're talking about a cooling curve, on the other hand, right, in which case it would be the mirror image of this, right? It would be something like, something like this, right? In which case, then potential energy would be decreasing the entire time as it's being cooled. Okay. Now, as far as kinetic energy is concerned, listen. Anytime you see the words average kinetic energy, that's the same thing as, you can literally cross it out and write the word temperature. And so if they ever ask you what's happening to the average kinetic energy, just ask yourself what's happening to the temperature. So I can see on this graph, if this is temperature and this is time, right? If they ask you what's happening to the average kinetic energy from A to B, well, it's obviously increasing because temperature is increasing. They ask you what's happening to the average kinetic energy at BC, what's remaining the same, but potential energy is increasing. They ask you from C to D, average kinetic energy is increasing. They ask you from D to E, it's remaining the same, but potential energy is increasing, right? So remember, potential energy is always increasing going in the forward direction if it's a heating curve, but kinetic energy will increase or remain the same depending on where in the heating curve you happen to be being asked about. Okay?
Mm-hmm.
Anything else?
Yeah, also the graphs that ask what's the relationship between temperature and pressure, and it has the like the lines. I don't really understand those.
Okay, good. All right, so you're talking about gas laws.
Yeah.
So, all right, so here are the different gas law relationships that you need to know. It's actually not that hard to memorize them because basically two of them are direct and only one of them is inverse. So what you basically need to know, I guess, or just memorize is which one is inverse, and then the other two are just going to be direct. The only one that's inverse is pressure and volume. The relationship between pressure and volume is inverse. That basically means that as pressure increases, volume decreases. If you have trouble memorizing that, just think of a piston type of device, right? So let's say I have, something like this, where a cylinder and a piston where I can pull up or push down on the piston. If I have a gas contained in this portion of the cylinder, as I push down on it, it's going to get harder and harder to push on the piston. I don't know if you've ever used a bike pump to pump up your tire. That's a similar type of device. As you push down on the plunger, it gets harder to push down the more you push. And the reason for that is because as you push down, you're pushing molecules closer and closer together. And so the more you push them together, the more they sort of repel each other. You can think of it that way, right? So as volume decreases, pressure increases. So it's an inverse relationship. Just memorize the, if it's having trouble understanding the concept, just understand that there's an inverse relationship between pressure and volume. The other ones are direct, and I think those are probably less difficult to remember. If you think about, and I think I gave you this example in class, if you take like an aerosol can, like a spray can that's filled with a gas, filled with air, let's say, and you chuck that can into a bonfire, let's say, right? That, I think intuitively you know it's going to explode, or it could explode. And the reason for that is because as the temperature of the gas increases, the pressure builds inside the can. And this is what we call a rigid container. This is a situation where volume is constant. If they ever use terms like rigid container, that means volume is constant. Although more than likely, they'll probably tell you what's constant. So basically, as temperature increases, pressure increases. The other one, the relationship between volume and temperature, that's also a direct relationship. So for that, just think of hot air. I don't know if that's the best example. Just trying to give you something to remember this with. If you ever have trouble taking off, let's say you have a spaghetti jar and you have a top on it, and maybe you're having trouble getting the top off. What people do sometimes is they run under hot water. And the reason that works is because when you heat up the metal, it causes the metal to expand. And by expanding, it actually makes it easier to take the top off. So just remember that as you heat a gas, it expands. So as temperature increases, volume increases. So again, two of them are direct, and only one of them is inverse. The only one that's inverse is PV. So if you memorize that that's inverse, and just remember that the other two are direct, you should be good with those types of questions. That's actually a really good question, by the way. Anything else? Anything else that sticks out?
Yeah, I have a question.
Yep.
Can you talk about what makes like a gas ideal?
Mm-hmm. Okay. So I mean, I could obviously just say to you, it's one of those things you could memorize, right? But I want to explain the concept. So there's something called the kinetic molecular theory of gases, often called KMT. And there's basically about 5 statements that I guess you're going to have to remember. And there's really no other way to, it's literally something you're going to have to remember. The thing about kinetic molecular theory is basically it's a model for how gases behave. It's essentially, it doesn't really represent the real world, but it's a simplified model that we use to be able to describe gases using ideal gas law types of formulas. So the statements are this: gases, gas molecules, the assumption is that they have very little attractive forces, have no attractive forces. And I'm having trouble writing this, but come on, no attractive forces. So that means the molecules are not attracted to each other. Okay. Now, in actuality, real gases actually do attract each other. But we say that ideal gases, they have no attractive forces between them. The other thing you need to know is that gas molecules are really far apart. And I'm trying to simplify this because I'm having trouble writing, but they're really far apart compared to their actual sizes. Okay? And those are probably the two most important things you need to know. Now, there are other things you need to know. And the other thing you need to know is that gas molecules are assumed to have no volume. The other thing is that they're assumed to move in straight line paths. The other thing is that they tend to, they're assumed to collide elastically. But all of those things are, I think, secondary to these concepts here, and that is that gas molecules have no attractive forces and that they're far apart. So now you ask yourself, under what conditions can you make a real gas behave as ideally as possible? So let's say I have a real gas inside this container, and I want to make the real gas sort of resemble these concepts here. They have no attractive forces between them. Well, I have two possible things I could do, right? I could either, again, if I have a cylinder here, right, a cylinder and a piston, the question is, if I want a real gas to behave as an ideal gas, do I pull up on the piston, or do I push down on it? And the answer is that you want to push up, you want to pull up on it. And the reason for that is because if I have a situation like this where the plunger is all the way down and I have gas molecules in here, that means these molecules are going to be really close together. And again, the assumption of the ideal gas model is that the molecules are really far apart. So we want them to be as far apart as possible. And so if I push down on the cylinder, on the piston, that's going to push them closer together. That's not good. The other thing that does, if I push down on the piston, that's going to increase the pressure. That's going to give me a high pressure, which I don't want. Again, if I want the gas to behave ideally, I want them to be as far apart as possible. So I want to pull up on the piston. So if I pull up on the piston, again, if volume increases, pressure decreases, right? So this is going to give me a low pressure. And if I have a low pressure, then the molecules are farther apart from each other, right, than if they were under conditions of high pressure, number one. And then the other thing you need to know is that molecules, when they're really close together, they have a tendency to stick. They have a tendency to be attracted to each other. Think of magnets, right? If I have magnets that are far apart like this, they might be attracted to each other, right? But if they're really close together and I have their unlike poles aligned towards each other, then they're going to be really attracted if they're really close together. So if I have molecules that are really close together, they're going to be attractive. So how do I minimize the attractive forces? Well, if I make them move as far apart from each other as possible, and I can do that by lowering the pressure inside the cylinder. The other thing that you can do to make a real gas behave ideally is increase the temperature. So there's basically two things, right? Real gases behave ideally under conditions of low pressure and high temperature. Now, what does high temperature do? Why does that make the gas behave as if they have no attractive forces and they're far apart? Well, you need to remember, if you increase temperature, that means the molecules are moving faster, right? And if they're moving faster, on average, the attractive forces between them will be minimized because they're moving around so fast. And that's because they're not going to be, on average, as close to each other as possible if they're moving around faster. So, again, if I have low pressure and high temperature, those two things will make a real gas behave as ideally as possible. And I mean, that's a lot to think about. That's a lot to think about for one question. For that, honestly, for that type of question, if I didn't want to think about all these things, I would just say, just memorize low pressure, high temperature. That's what you need to know. Low pressure, high temperature. That makes a real gas behave ideally. And that's pretty much it. Now, obviously, they can flip that, obviously. They could say, under what conditions will a real gas deviate the most from ideality? Obviously, then it'll be the opposite of that. The answer would be high pressure, low temperature. But just memorize, again, I'd like you to think about the concepts, but there are times when just the concepts just don't come to you. And so, I don't know, LP, LPHT, I guess, turn it into like an acronym. Make that mean something to you. I don't know what you could do, but just make that mean something. LPHT.
I use
Go ahead.
like if you want to like a vacation, and like the ideal way to go is like having low pressure and like having a warm vacation, so high temperature.
Right. The only problem, the only problem with that, the only problem with that, you know what? Go with that. Go with that. The only problem with that is low pressure systems. Low pressure usually doesn't bring you good weather. If you ever watch like weather channels,
I'm talking about like
It's stress.
pressure from work.
Okay, all right, okay, that's a good idea. Yeah, absolutely. That'll work. That'll work.
Wait,
Okay.
Mr. Green, on
Yeah.
the Regents, do we have to know like London dispersion forces and all that?
Yes, you do.
What is that?
Okay. Okay. Wow, that's a big question. Okay, so that's what we call an intermolecular force of attraction. Okay?
Wait, inter or intra?
Inter.
Okay.
First of all, intermolecular forces are between molecules. Between molecules. These are attractive forces between molecules. There's a few different ones that you have to know. Sometimes you just call them van der Waals forces. I don't know that van der Waals forces are easier to remember than London dispersion forces, but there's a few that you need to know. LDFs, dipole. Come on. Ion dipole. And H bonding. Okay? Those are the only
Hydrogen
ones.
bonding is only with like nitrogen and like fluorine.
Exactly. Well, okay, nitrogen, oxygen, and fluorine.
Oh, okay.
And by the way, the thing you need to remember about that is that this one is the strongest on average. Okay? London dispersion forces are the weakest. Now, let me just add a little caveat here. Like, I don't think you will ever, in fact, I don't think I've ever seen the words London dispersion forces. No, I'm going to even go further. I have never seen the words London dispersion forces on any Regents exam in almost 20 years of teaching. That said, you do need to be aware of them, and they don't really care if you use the words London dispersion forces, but you do need to know that they're weak, and more importantly, you need to know what types of molecules are held together by LDFs. Do you remember which ones?
Isn't it like polar?
No.
No.
I'm glad you asked that question. These are
No, it's covalent, right?
These are non-polar molecules only. Only. Non-polar. I'm actually glad you asked that question.
So
That
like,
could-
wait, CO2?
Exactly. Yeah. There are honestly, there's a few different compounds that you can save yourself a lot of time if you just memorize their structures. CO2 is one of them. There's a lot of nonpolar molecules. CO2 is one. Methane is another. In fact, any alkane, any normal straight chain alkane, is nonpolar, and I'm talking about the molecule now, right? The way we ascertain polarity as far as molecules are concerned we're going to use the symmetry argument. And that is that if you can cut the molecule in half two ways, vertically and horizontally, if there's a line of symmetry, in which case, both sides of the molecule are the same. If you cut it in half vertically and horizontally, we say that molecule is nonpolar. Remember, it has to exhibit at least two lines of symmetry, at least two. And that's how we define a nonpolar molecule. So just remember that if it's nonpolar, those molecules will be held together by London dispersion forces, which are the weakest ones. And by the way, that explains why carbon dioxide and methane are gases, because the forces holding those molecules together are very weak. And again, we just finished talking about that. Gas molecules are assumed to have no attractive forces between them. Now, in actuality, that's not true, but London dispersion forces are pretty weak. So that's as good as having no attractive forces between them. So you need to know that nonpolar molecules interact through London dispersion forces. Now,
wait, I'm really confused. So now IMFs only have to do with the molecule and not the bonds between elements?
It never did. It never did. Okay, the problem, I think, is because you have terms that sound really the same. I think that's the problem. You have what are called intra. I almost regret even mentioning this because it probably made it more confusing, but you have intramolecular forces and then you have intermolecular forces, okay? So intermolecular forces, that's what I was just telling you about. Those are what we call IMFs, and that's between molecules. Now, intra, just look, the word A, that's between atoms. So what am I talking about here? I'm talking about covalent bonds, right? Or ionic bonds, okay? And those, by the way, those are always stronger. Intramolecular are always stronger than intermolecular. So covalent bonds and ionic bonds are definitely stronger than any of these intermolecular forces that we just talked about.
Wait, but hydrogen bonds I thought had to do with the certain elements, not molecules.
Okay. I'm telling you, you're probably adding points to everyone's score by asking these questions. That's a good question. So what are hydrogen bonds? So again, hydrogen bonds are are attractive forces between molecules. So for example, if I have H2O like that, H2O will interact with itself through hydrogen bonding. So how so? Well, you need to remember that oxygen is more electronegative than hydrogen. I don't know what it is. I think it's 3.5, the electronegativity, but I don't know exactly. I think hydrogen's 2.1. So because of that, this bond is a polar. Let me just be perfectly clear. This bond here is a polar covalent bond. And that's because there's an electronegativity difference between the oxygen and the hydrogen. There'll be a partially negative charge on the oxygen and a partially positive charge on the hydrogen. And that's always true of elements that have lower electronegativities. They're always partially positive. So if I have another water molecule nearby, it's going to be attracted to that water molecule, the one that I drew above. And for the same reason, there's a partially negative charge on the oxygen, there's a partially positive charge on the hydrogen. So you should remember that opposite charges attract each other. So the partially positive hydrogen will be attracted to the partially
okay.
And that's a hydrogen bond.
Yeah.
H bond. So, but that only happens, right? This only happens if hydrogen is connected to a highly electronegative element.
I see.
X must be nitrogen, oxygen, or fluorine. Okay. Now you might think, well, what if I have something like this, sulfur, right? Sulfur, dihydrogen sulfide has literally almost the same structure as water, and it should, because sulfur is in the same group as oxygen. So you might ask, well, can't these molecules interact through hydrogen bonding? The sulfur is going to be partially negative, the hydrogen is going to be partially positive for the same reason that, same situation is over here, right? So you might ask, well, isn't that a hydrogen bond? Well, apparently that attractive force is not as strong as what we would call a hydrogen bond. I can't really get into why that is at this particular moment. That's for AP, but basically you need to know that unless this atom here connected to hydrogen, unless it's nitrogen, oxygen, or fluorine, that's not considered a hydrogen bond. Now this attractive force here is what we call a dipole attraction. And the reason we call it dipole is because this molecule is what we call a polar molecule. It's polar because it does not have symmetry along two planes or along two lines. It has vertical line symmetry. If you cut it in half that way, it's symmetrical, but it doesn't have horizontal line symmetry. So we would say this molecule is what we call a polar molecule. Another way of referring to a polar molecule is calling it a dipole. Dipoles are polar molecules. And so this attractive force between the two dihydrogen sulfide molecules, this is what we call a dipole attraction. And in the grand scheme, dipole attractions are actually not as strong as hydrogen bonds. Okay, in terms of strength, it's actually second in line. It's stronger than an LDF. Now this thing here, ion dipole, what is that? That's really important. You need to know that this. I'm sorry. You're gonna say?
I'm still confused about a dipole a little bit. Like, what's a dipole? One more time.
Okay, one more time. I'm sorry.
Like, what's a dipole? Okay,
dipole attraction is an attractive force between two polar molecules. By the way, I'm assuming that you understand what the word polar means. Polar basically means it has a positive end and a negative end. So just say, if you know magnets have a north pole and a south pole, right? There's a positive side and there's a negative side, right? And I think we know from middle school that if you put the positive side of a magnet close to the negative side of a magnet, they're going to attract. Well, molecules are like that too. They have a positive side and they have a negative side, right? So if I have two molecules that have a positive and negative side like that, they'll be attracted to each other. That's called a dipole attraction. Now again, why would a molecule have a dipole? Again, as I said before, if one of the atoms has a partially positive side and the other if one atom is partially positive and the other atom is partially negative, and they're on opposite sides of the molecule, that molecule is considered a dipole. So here's another example of a dipole, HCl. Hydrogen is less electronegative than chlorine, and so electron density will be pulled towards the chlorine. So this will be partially negative. This will be partially positive. So this molecule looks something like that. Okay? So if I have another hydrogen chloride molecule nearby, right? Same thing. This is going to be partially positive. This is going to be partially negative. They're going to attract each other. That's called a dipole attraction. The two molecules, they have to be polar. And how do I know if a molecule is polar? If it's not symmetrical, right? If it's an asymmetrical molecule, we assume that molecule is polar. And so it can interact with itself through dipole attractions. Now, sometimes, I don't want to confuse things, but sometimes that dipole attraction is called hydrogen bonding. That's the thing I think what makes it confusing. Because if you look, water is polar. And so if it's polar, that means it's a dipole. And so that means it can interact with itself through dipole attractions, except we don't call it that. We call it hydrogen bonding. Hydrogen bonding is just another type of dipole attraction. It's a stronger type, but we just happen to call it by a different name for some reason. Um, did I explain that? Did I answer
Wait,
your question?
so LDFs are bonds between two nonpolar? Is that all
That's it.
it is?
Okay, let's be. Let me just. It worries me a little bit the way you just said that. You call it a bond. Um, Remember, a bond is not a bond is not an intermolecular force. A bond is what we call an intramolecular attraction, right? It's much
Yeah.
stronger than an IMF. So just be aware that it's an attractive force between molecules. Just try not to call it a bond. Now
Okay.
again, if I'm grading that, I understand what you mean, but I don't know, the person grading it will say, "Oh, wait, you call it a bond, and that's wrong." Um, just be aware that an intermolecular force of attraction is just that. It's an attraction, but it's weaker than what we call a bond.
Yeah.
It's like it's like minutia as far as I'm concerned, but I just don't want you to lose points based on somebody misinterpreting what you wrote. Um, anything else? Anything else? Stuff that
Yeah, what is the ionic dipole thing?
Okay, I'm sorry. You were absolutely right. I completely got off track here. Ion dipole. Yeah, that's really important. So that is what it sounds like. It's an attractive force between an ion and a dipole. The most common example of that, in fact, I'm going to almost bet my house that the only time you're going to see that is if they ask you about the attractive force between, let's say, a salt ion and water. So remember, water is a polar molecule. That means it has a negative end and it's got a positive end. And so what you need to know about that is that if there are any ions in an aqueous solution, there will be ion dipole attractions in that solution. And that because of that, the reason for that is because oxygen, again, has a partially negative side. Sodium ion, in this case, is a partially positive, so there'll be an attractive force. That's called an ion dipole attraction. Again, it's an ion and a dipole, right? So if I have water molecules, a lot of them, and I always would, of course, if I have an aqueous solution, they're going to surround positive ions like this, right? I think I called water molecules bouncers in a club, right? And there's a reason for that, because they literally get in and they'll surround any type of ions that are in an aqueous solution. Now, normally ions, they like to bond to each other. So for example, if I have a sodium ion and a chloride ion, and they're near each other, they want to bond together. They want to bond together and form sodium chloride, which is an ionic compound, right? But if I have water molecules that are present, if I have any water molecules that are present, that's not going to happen, because water molecules will surround each of the ions and keep them separated. Again, just like bouncers in a club, right? So if I have a chloride ion that's present, water molecules will also surround them, but they'll surround them differently. And hopefully you can see why, right? Again, because water is a polar molecule. And so it also has a positive side, like that. So it's going to interact with the negative ion like so. By the way, this process is called hydration. I don't know if I called it that in class, but when water molecules surround an ion, that's called hydration. And these attractive forces that you're seeing here, these are ion dipole attractions. All right. I don't think they're going to ask you. I'll almost promise you, they're not going to say what's an ion dipole attraction. They're not going to even mention that. But you do have to be aware that they exist. Anything else?
Yeah. Organic reactions. Can you just go over those?
Okay. Yeah. Absolutely. Okay. So organic reactions. I think there are 5. I'm not sure exactly how many. Let's talk about that. So let's see. So we got saponification. That's probably the easiest one to remember, I think. In fact, the only thing they're ever going to ask you about that is they'll probably ask you like, by the way, does anybody remember what that is?
Oh, it's when it makes soap.
Exactly. It's a making of soap. And that's how they're going to...
Glycerol.
Exactly. Yeah. Okay, wait. It's they're
Is it
gonna,
like actual soap, like the soap we use?
yeah, exactly. They're gonna ask you, which process refers to the making of soap or something to that effect. That's one possible question they could ask you. They could ask you what it's made from, as well. And I guess you need to know that as well. And so, does anybody remember what that is? What do you make soap from?
Like fat or
Fat.
something like
Yep,
that.
fat
Fat
and the base.
base.
That's it. This is a very simplified version, but that's all it is. By the way, the other thing you need to know, and this is rare, right? But I want to give you every possible chance you have to get 100. The other product that's produced in the making of soap is glycerol. I think I heard somebody say that. Glycerol. And so glycerol, that's that molecule. You need to memorize. You need to remember it. Again, this is rare. This is really rare. I'm just trying to. I want to give you every possible shot, to get the best grade. So that they may ask you, what this compound is, and this is it.
That's
Glycerin,
right?
it's a glycerin or glycerol. It's a trihydroxy alcohol. 1,2,3 propane triol. They also call it that. They're probably not going to call it that. But that's it. That's all they're going to ask you about saponification. It's the making of soap and the process makes soap and glycerol. That's it. All they're going to ask you. The other one that's easy is fermentation. Fermentation. That's the making of alcohol. Making of alcohol. And I can promise you, the example that they give you will literally, if you see it, it will be this. It will be this reaction. It will be C6H12O6. By the way, I should say it's the making of alcohol from sugar. And the sugar, it doesn't have to be glucose, but I'll promise you it's going to be glucose, C6H12O6. And then what they sometimes do is above the arrow, they write the word zymase, which is an enzyme that I guess yeast uses. This is made with yeast, by the way. Yeast will eat the sugar and basically make ethanol by one process, by one pathway. You need to know this form of ethanol. You need to know that it has this formula. That's probably the only tricky part of this whole question. You need to know that ethanol has that formula. The complete structural formula is this for ethanol, but they may not give you that. They may give it to you like that. You need to know that that's ethanol. That's not hard to remember because you see an OH here and you see 2 carbons. That's definitely ethanol. Plus, by the way, carbon dioxide. And this needs to be balanced, which I probably need. I think I need a 2 here, and I think a 2 here. That probably balances it. Yeah, that balances it. So I promise you that if you get any questions about fermentation, this reaction right here will be the reaction that you see. Because it's never been any other reaction in, like I said, in the last 20 years that I've taught this course. So, all right, so that's fermentation. The other type of organic reaction is combustion. I don't think you guys are going to have any trouble with that because we were talking about combustion a long time ago. So combustion reactions always look something like this. You see some kind of a hydrocarbon, and I'm going to write it like that because it could be any hydrocarbon. And that's a hydrocarbon. We just don't know what X and Y are, but it will be the combination of a hydrocarbon plus oxygen to produce carbon dioxide in water. So what makes it combustion? It's because you have a hydrocarbon that's combining with oxygen. Basically, it's being burned. Combustion means burning. And when you burn something, you're combining it with oxygen, right? That's why you need oxygen in order to support burning. But what's going to happen in every combustion reaction that you're going to see is you're going to get the production of CO2 and H2O, okay? And that's how you identify it. It's got to be a hydrocarbon, number one. I'm just I'm thinking. I'm 99% sure it's going to be a hydrocarbon. It doesn't have to be. It will always be some kind of organic compound. It could be an alcohol. It could be like CH3OH like that, plus oxygen. Because you can also burn alcohols, right? You can burn a lot of different things, but I'm just giving you examples of what you're going to see. So those types of reactions are combustion reactions. Again, what makes it combustion? It's an organic compound combining with oxygen to produce carbon dioxide. Okay? Those are the only types that you'll ever see. But I'm pretty sure it's going to be like that. The one on the top, it's going to be a hydrocarbon. It's probably not going to be alcohol. Okay? So that's combustion. Let's see. Addition. Addition. Do you guys remember what that is? Okay.
Isn't it like the addition of a like halo or something?
Okay. So let me go over that. So the addition is literally, it's a synthesis reaction. Okay. First of all, it's a synthesis reaction, which basically means you're going to have two reactants and basically one product. Okay. But it's a specific type of addition reaction. It's an addition reaction with an unsaturated hydrocarbon. And by that, I mean one that contains a double bond. So it's going to be either an alkene or an alkyne. I'm going to say 99% of the time it's going to be an alkene. But what's key here in an addition reaction is that basically what you're doing is you're adding some kind of a diatomic molecule. And by that, I mean it can be H2, or Cl2, or Br2, right? Or, I mean, honestly, it can be, those are the only ones you're probably going to see, right? But in an addition reaction, what you need to know is that if it's a diatomic molecule, like let's say Cl2, what happens is that molecule literally is added across the double bond. In other words, one atom goes there, and one atom goes there. Okay? Now, if you look at that long enough, you should be saying, well, carbon already has 4 bonds here. It's got 1, 2, 3, 4 bonds. It can't make another bond with a chlorine atom unless the double bond is broken. So what you would get in the case of an addition reaction is you get a breaking of one of the bonds, and you have an atom of each of the molecule that was added to 2 different carbon atoms. That's why I say it's added across the double bond. So this is what we call an addition reaction. So like I said before, it's a synthesis reaction. I have 2 molecules, right? In this case, ethene and chlorine, right? Being added together to form this molecule here, which of course is 1,2 dichloroethane. Okay, so again, to summarize, it's a synthesis reaction involving an unsaturated hydrocarbon. It has to be, that's really key, it has to be an unsaturated hydrocarbon. If it's not an unsaturated hydrocarbon, it's not going to react by addition. So by unsaturated, I mean either an alkene or an alkyne. And it can be any of these molecules. Any of these molecules. By the way, it could also be HBr. Something like that. That can also add across the double bond. Okay, so that's addition. Now, in contrast to that, there's something called substitution. And substitution, this will generally happen with saturated hydrocarbons. Okay? Got to be saturated. It actually, in actuality, doesn't have to be, but the only ones they're ever going to ask you, they'll be saturated, which means any alkane, right? So in other words, it could be methane, or it can be ethane, right? Ethane. In other words, molecules that have all single carbon-carbon bonds. By the way, these sticks here are hydrogens, right? I don't always put them in, but assume they're hydrogens. So what does that look like? Well, in a substitution reaction, first of all, it will always be some kind of a halogen. It's always going to be bromine or chlorine or iodine, right, etc. It'll be probably one of those three, or fluorine, right? And in a substitution reaction, what literally happens is one of the hydrogens is substituted for or replaced by an atom of the halogen. So basically, in this reaction, any of these hydrogens could be substituted for. So what I would get, go ahead, I'm listening.
Isn't that called like if it was with Br2, isn't that called like bromification or something like
Yeah,
that?
yeah, you could call it that. Yeah, I mean, usually that term is used for addition reactions, but yeah, you could call it that. I mean, no one's gonna penalize you if you do. But the key here, guys, this is really important. If only one of the hydrogens is replaced, I have another one that's left. So where does that go? Well, the hydrogen that's replaced, it bonds with the other halogen atom. So what you're always going to get, and this is really key, this is how you're going to identify it. You're always going to get some kind of a hydrogen halide, like HBr in this case. It could be HCl, right? If you use Cl, it could be HI, right? If you use iodine. But that's really one of the dead giveaways. If you see a hydrogen halide at the end, that's probably going to be a substitution reaction. But the other key here is that this has to be a saturated hydrocarbon, right? In other words, if this is ethene, like that, if this is ethene, let's say, and you react this with chlorine, like I did before, you're not going to get a substitution. You're not going to get one of these hydrogens substituted for it. What's going to happen is that you're going to break that bond, and this reaction will occur through the addition mechanism, not by substitution. Okay, that's really important. Okay, so that's substitution. Let's see, what else is there? So there's polymerization. Okay, and there's only two types. Well, come on, I can spell polymerization. Polymerization. There's two types. Unfortunately, this is a confusing thing. There's a type of polymerization called addition. There's addition polymerization, and then there's something called condensation polymerization.
Wait, okay. Is this an organic reaction or no?
Yeah, these are organic reactions.
Okay.
Yeah. Polymerization is another type of organic reaction, but unfortunately, there are two types of polymerization reactions. One is called addition polymerization. The other one is called condensation polymerization. Okay. Now, I'm going to tell you that if I'm 99% sure that if you see a polymerization reaction, this is what it's going to be. You're going to see this molecule, which is, again, this is ethene. Oops, come on. And then you'll see a reaction, an arrow like this. And they might, I guess it would give it away if they wrote the word polymerization over it. But if they didn't, and instead you see a product like this, and then you see, brackets around like that, and then like N equals, a large number, let's say. This is what we call addition polymerization. And why is it addition polymerization? Basically, what you need to know, first of all, polymerization, the joining of several small molecules to form a very large one. That's what polymerization is. So, and the small molecule that you're starting with, that's called a monomer. Okay? And the molecule, the giant molecule that you end up with, and it's a huge molecule. This is called a polymer, right? So basically, polymerization is the joining of several small molecules called monomers to form a huge molecule. So it's very difficult to show this monomer being joined together to form a huge molecule. The only way to do that is they'll show you this structure that contains the monomer. Notice that one of the bonds is broken, and the reason that the bond is broken is so that this monomer can form bonds with other monomers on both sides. But this happens thousands of times, and so you end up with something that's a polymer. I'm like 99% sure that if you see this reaction, that if you see polymerization at all, addition polymerization, it's going to be this reaction. They always show this one.
What would the question be asking though? Like, would it be a multiple choice and be like, what
It could be
organic reaction is
absolutely,
this?
absolutely. It could be identify this type of reaction. It could be, what do you call the product?
Yeah.
And the choices could be, an ester, an ether, a polymer, any organic type of molecule. You just need to know that in a polymerization reaction, a polymer is formed, and a polymer is a very large molecule. So, but notice that this process occurs by adding several molecules together. I wish I could show you the mechanism. It would be very complicated for me to show you. I think I showed it to you in class, or I think I was about to, but basically you have a lot of these monomers being added together, almost like, think of it this way. Think of polymerization as occurring like a monomer is a pearl, right? And imagine that several pearls being, strung together, added together to a string until you end up with a string of pearls, right? So that string of pearls is called your polymer, except in this analogy, this pearl necklace would contain like 1,000 pearls, right? Or 2,000 or 3,000, a big number. That's what you need to know about polymerization, or addition polymerization anyway. And then there's condensation polymerization. So how does that differ? Does anybody remember? How does condensation polymerization differ from addition polymerization? Anybody?
It's like something with water.
Yeah, exactly. So, okay, so that's honestly what you need to know. So here's an example of a monomer, right? Let's just call this a monomer. It's a small molecule that I can join together with several of these same molecules, right? So let's say I have this same molecule on the other side, like that. So how could I join these two molecules together? Well, if you look closely, I can do something almost like a dehydration synthesis, if you guys remember that from last year. Basically, it's a process in which you join two molecules together by taking out water. So if you look, basically I have two OHs next to each other. If I take out water between them, right, then what I end up with is a molecule that's larger than before, like that. Now it's got 4 carbons, okay, and the rest of these are hydrogens, right? Actually, I screwed up. There should be an oxygen in between here. So there should be an oxygen here, right? And a bond there. And then the other thing here, since I took out water, water would be a product. That's the dead giveaway in condensation polymerization. In condensation polymerization, you end up with a polymer plus water, okay? By the way, this right here, that's really not a polymer per se, because a polymer is a large molecule. So I wouldn't call that a polymer just yet. But if I did that several thousand times, let's say, then I end up with something called a polymer. But the key here is that if I end up with a polymer plus water, that's what identifies it as condensation polymerization. Okay? So again, there's 2 types. There's addition polymerization, and there's condensation polymerization. In addition polymerization, all I end up with is just a giant polymer. But in condensation polymerization, I end up with a giant polymer plus water. And that's really what distinguishes the two types of polymerization from each other. All right, so I think there's two more. No, there's one more. There's esterification.
Is there like another half of this will keep? Yeah, sure. Yeah. But you have to pay it.
I think there's somebody who just came in. Because I'm hearing. We're waiting for the name.
Oh wait.
I think it's Emma
Okay. Emma
Anderson.
Yes,
Anderson.
yeah, I think it's
Okay.
Emma. Of course it's Emma.
Emma Anderson, identify yourself. Yeah, okay, it's Emma. Well, that narrows it down to at least 4 people, because I think I had 4 Emmas.
No, it's Emma Anderson because she
Okay.
just logged on to Skype.
Okay. All right, so, all right, guys. So esterification, what is that to you?
The making of an ester
Making
out of an acid and alcohol.
There we go. It's the making of an ester.
Thanks.
These things basically they kind of are what they sound like in a lot of cases. Of an ester, ester. So what's an ester? Well, an ester, first of all, is a compound that contains a C doubly bonded to an O, bonded to another oxygen, and then on that side, that has to be a carbon. So basically, that's this group right here is what makes it an ester. But the key here, and it's what Haley just said, it's from an acid, an organic acid, and an alcohol. Come on. Okay, so that's basically what it is. I can give you an example of that. I've never seen them ask you what type of ester would be formed, but that doesn't mean that they won't. So I'm going to give you something like that. So let's say I have this alcohol. Come on. And let's say I react this with, need an OH there if that's an alcohol. And let's say I react it with this organic acid. Okay. So how do I figure out what the ester is that will be formed? Pretty easy. Pretty much what you do is what I did in the last example. You basically take out water between the two molecules. You do that by putting the OH. They may not give it to you like this with the molecules oriented in the right direction so that you can figure out what to take out. But all you do is you put the OHs next to each other. So if you have an organic acid, that might be flipped the other way. Just turn it around so that the OH is facing the OH of the alcohol, and then just take out water between them, like that, and then just bond what you have left. So I'm going to get this compound, like so. And then, right, plus water, of course, right? If I'm taking out water, right? And that's pretty much it as far as esterification is concerned. Again, it's got the COO in the middle, and that's what makes it an ester. I just came across a question earlier today regarding esters. You need to remember that esters, they smell really sweet. That's one of those sort of property questions that they ask you about as far as different compounds. They want you to know that flavors and perfumes, things like that, they tend to be esters. And that's pretty much it as far as esterification is concerned. And that's all of the organic reactions, if I'm not mistaken. I don't think there's anything else. Yeah, I think I hit them all. Anything else?
Can I ask you a question that was on one of the practice Regents I took?
Yep.
I don't know.
Absolutely.
Okay.
Absolutely.
It was it was a short answer and it had
Okay.
a equilibrium equation.
Okay.
And then the question said, use the key to draw two water molecules in the box, showing the correct orientation of each water molecule toward the chloride ion.
Okay.
So, like, what do they? I don't understand like the orientation part.
Okay.
Like,
So yeah, see, it's okay. So it's what I said to you before. Remember, water is a polar molecule.
okay.
It's got a negative end. It's got a positive end. You need to know that the oxygen has a partially negative side, hydrogen has a partially positive side. And so if they're asking you for the orientation of the water molecule relative to chloride, I guess if they didn't tell you, they expect you to know that chloride is negatively charged. And because it is, the hydrogens will be pointed at the chloride like that. In other words, if you did this, you do that like that, that would be wrong because oxygen has a partially negative charge and it wouldn't orient itself relative to chloride like that because it would repel it, in fact. So they expect you to know that water molecules would orient themselves around a negative ion like so, with a hydrogen pointed at it. So they ask you for just two molecules, that's what you're going to do. Now, in actuality, there'd be more than two, but since they're only asking you for two, you do two. But it would completely hydrate the chloride ion. It would completely surround it.
Okay.
Like that.
Do you have to draw any like dotted lines to
No.
indicate there is attraction?
No, you don't have to. If they're just asking for the orientation, that's it. But by the way, generally speaking, a dotted line like that always means intermolecular force of attraction. And that's just to convey that attractive force is less than an actual bond, like a covalent bond, in which we draw with a solid line like that. Anything else?
Yeah. What kind of questions would they ask for titration? Like, would it just be part 2, like math questions?
That's a really good question. I honestly, they tend to be part 2 questions. You want to know the truth? I don't think I've ever seen a part 1 question. I don't think I've ever seen a titration question that wasn't part 2. And so I think I have one here, as a matter of fact. Let me just see. I think I remember seeing one here. Let's see. Did I just them out? There we go. Okay. 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 Here we go. Yeah, there we go. So this one here, it says in another trial, 40 milliliters of HCl is completely neutralized by 20 milliliters of this 0.10 molar NaOH. Then it says calculate the molarity of the titrated acid in the trial. So this is the type of question that they would ask you with titration. And so,
Isn't this on the reference table?
yeah, the formula is on the reference table.
Yeah, reference table P.
Yes, and that is that one. Come on, where are you? This one right here. MAV equals MBVB. And so you just have to ask yourself, what are they asking for? Number one, they're asking you for the molarity of the titrated acid. So that would mean Ma to me. And so, MAVA equals MBVB. I've never seen that in like a part 1. It's always the first time for everything, but I don't think I've ever seen that before. So you're being asked to solve for Ma. So Ma is equal to MB VB divided by VA. And you plug in. So it says neutralized by 20 milliliters of this 0.1 molar NaOH. Hopefully, you know that's MB, 0.10 molar. And the volume of the OH is 20 milliliters, 20.0. And VA, it says 40 milliliters of HCl, so that's 40 milliliters. Come on. And so, so that they're just asking for the setup. So there we go. There's a setup. If they ask you for the answer, you're going to round this to 2 sig figs because 0.10 only has 2 sig figs. And this is easy because it's just 0.10 divided by 2, it looks like. So this, if I can do my math properly, this is 0.050 molar, I think. Right? Notice that I added a 0 at the end because I need 2 sig figs. That 0 there is a placeholder. It's not significant.
But sig figs will never matter on the Regents, right?
I can't say that. In this case, it doesn't matter because they don't ask you for it. But there are questions where they say, express the answer with the correct units and the correct number of sig figs. So if you gave me, let's say for the sake of argument, let's say you wrote 0.05 like that, you'd probably get 1 point, and you lose a point for sig figs because there has to be.
You mean if they ask for sig figs?
Yeah. If they ask for it, you do it. But if they don't, then they don't care about sig figs.
Yeah.
And I'm going to say like 99%, and sometimes actually even 100% of the questions, they don't care about it. But every now and then, they will say, express the answer in sig figs. I don't even know why we teach it, to be honest with you. We're just preparing you for the Regents. But next year, some of you will take physics, and you will do everything in sig figs. So that's probably one good reason for why we do it.
Wait, for neutralization reactions, is that when an acid and a base like neutralize each other and create but doesn't something like water have to do with it?
Yeah, exactly. So in this case, right, first of all, this formula here that you use, this is the titration formula. And usually when you do titrations, you titrate to neutrality. So it's a neutralization reaction that this formula is referring to. And so in this particular case, and by the way, the only types of titration reactions, you can titrate many different things. Not every titration is an acid-base titration, but the only ones you'll ever see, the only titrations that you'll ever see will be acid-base titrations, in which case you're titrating to neutrality. And so it's always the reaction between an acid, in this case HCl, and a base, which in this case is NaOH. And neutralization reactions are always double replacement reactions. Okay, so if you want to figure out what the products are, all you do is you break your acid apart into its ions, break your base up into its ions, and then do a double switch. So HCl is an Arrhenius acid in water. It H plus and Cl minus. NaOH is a base. It's an Arrhenius base. It will produce Na plus OH minus. And as I said, neutralization reactions are double replacement reactions. You put the positive ion with the negative ion on the other compound, the positive ion with the negative ion on the other compound. And so what you're going to get in this case is NaCl, which is your salt, which is what's always produced in a neutralization reaction. You get a salt, plus, by the way, you get water. So sometimes they'll ask you what the salt is. If they ask you what the salt is, you want to break your compounds up into their ions and do a double switch, do a double replacement, and you'll figure out what the salt is pretty easily. That's usually, I can't say usually, that's sometimes a part 1 question where they'll ask you what the salt is, but I've seen part 2 questions where they ask you that as well.
I get that confused with like the Bronsted-Lowry thing, because
Yep. Okay. Okay. Yep. We can go over that. Okay. So there's 2 acid concepts that you need to know. Acid-base concepts. There's the Arrhenius concept, and then there's the Bronsted-Lowry concept. First of all, they're probably not going to call it Bronsted-Lowry. So you can almost forget that. They probably call it alternate theory. Okay, that's probably what they're going to call it. They stopped calling it Bronsted-Lowry a while ago for some reason. I don't know why. So here's what you need to know. For acids, an Arrhenius acid is a substance that produces H plus ions. H plus in water. And I'm abbreviating this, like I'm trying to write it as simply as possible just because my pen is just really acting up. But basically what I want to say here is that acids, Arrhenius acids, produce H plus ions as the only positive ion in water. Okay? Arrhenius bases, on the other hand, produce OH minus. Okay? Come on, in water. As the only negative ion. And so Arrhenius acids must contain H, number one, like HCl. And Arrhenius bases must contain NaOH. Must contain OH. Okay, let me say it again. Arrhenius acids must contain H. Arrhenius bases must contain OH minus. Okay? Now, Bronsted-Lowry, that's a little bit different. Again, you have the acid and base concept again. But this has to do with donating. So in a Bronsted-Lowry acid is what we call a proton donor. Donates a proton. Okay? A base is a proton acceptor. And most likely...
Wait, when do they donate and accept protons?
Okay, I'm going to give you an example. Okay. More than likely, what they'll do with that question, if they ask you anything about Bronsted-Lowry, it's almost always with respect to an actual reaction. Like they'll ask you to look at a reaction and identify the Bronsted-Lowry acid or base. So for example, let's say you have this equation. Which, by the way, is an equilibrium.
Mom said they'd be home soon. No, they went to go to the stronger
Like that.
graveyard, but
Okay, so here's a reaction. And they might ask you, okay, so which species in the forward direction is a Bronsted-Lowry base? And so what you do is you ask yourself, what's happening with the proton? And this is actually a really, really easy question because you just have to basically look at the reaction and figure out what's happening with the proton. So if I look at it, I start out with NH3 over here, and somehow or another I end up with NH4. So this must have gained a proton somehow. It must have accepted a proton. I know that because it went from NH3 to NH4. So because this is accepting a proton, it must have accepted a proton because I see it becomes NH4 plus. This is what you call a Bronsted-Lowry base. Now, where did this get the proton from? Well, it got it from H2O. Proton must have went that way. Okay? So, and I know that this must have donated a proton because over here, I have OH minus. So how does H2O turn into OH minus? Well, if H2O loses a proton. Now, it doesn't just lose it, it transfers it. So because it's transferring a proton to NH3, this is what we call a Bronsted-Lowry acid. Okay? So if they ever ask you anything about Bronsted-Lowry acid or alternate theory, they will almost always give you a reaction and you'll just have to look at it to figure out what's happening. Now, this is an equilibrium, which means that the reverse reaction can also occur. So tell me, which one of these species, ammonium or hydroxide, which one is a Bronsted-Lowry, which one is a Bronsted-Lowry base? Which one is the acid, which one is the base?
The acid is NH4.
Absolutely.
Right.
And I know that because, again, looking at the reaction in the reverse, right? NH4 is turning into NH3. How does that happen? This must lose a proton. It loses a proton to OH minus, so it goes that way. Okay. Sometimes they ask you about acid-base conjugates. Although I haven't seen a question like that in a long time. If they ask you about the conjugates, you need to know that NH3 and NH4 plus are acid-base conjugates. Or you could say H2O and OH minus are conjugates. Do I need to explain that?
Yeah, what
No.
is a conjugate?
Okay, a conjugate is basically, conjugates basically differ by one proton. Or another way of thinking of it is a conjugate is what the species turns into after it either gains or loses a proton. So in other words, NH3 after it gains a proton, it turns into NH4. And so because of that, they're what you call conjugates. Okay? H2O, once it loses a proton, it turns into OH minus. So conjugates are basically, again, they differ by one proton. Or another way to think of it is it's what the species turns into after it either gains or loses a proton. I mean, the likelihood of them asking you that question, I have to say, is low. But again, I'm just trying to every possible, question they could ask you as far as acid base is concerned. Anything else?
Yes.
Okay. Okay. I'm glad you have any questions.
Okay, the electron dot structure, like
Yep.
with metals,
Yep.
like with
Okay.
like the brackets and stuff. I don't know
Okay.
how to do
Okay.
that.
So for example, if I ask you for, let me not use that one. Let's say if I ask you for the electron dot structure of CuBr2, give me the electron dot structure of copper 2 bromide. So go ahead, try it out first before we talk about it.
Wait, what do you want us to do? I'm a little confused.
Electron dot structure.
Oh, okay.
I gotta say, if you're still here, your stamina is amazing. At the same time, if you don't warn me, we'll be here for 5 hours.
I don't remember. Never mind. Hold up. I think I got it.
Okay. Well, first of all, it's ionic. The reason I know it's ionic, metal and a non-metal. Number one. If it's ionic compound, got to use brackets. And so this compound does not contain any polyatomic ions. That means they're all monatomic ions. And so if I look at the number of atoms, I see that I have 3 atoms, which means I need 3 brackets. So first thing you do is you put the metal atom in bracket, or the positive ion in brackets. You have to know what the charge of the ion is. That's really important. That's probably the hardest part of this. What's the charge of copper here?
2.
+2.
Plus 2. You do that. Br2, that's not a polyatomic ion. That just means I have 2 bromide ions. And so I have 2 brackets for bromide, like that. One thing you need to know. Go ahead.
Is it okay if I put 1 bracket but indicated like the 2 on the
Yeah,
bottom?
that's fine. Yep, I showed you that way as well. I'm going to show you that too as well. So, but the one thing you need to know about the nonmetal is that it always, 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 always gets 8 dots around it. Don't forget that. And then the charge on the outside like that. Always.
Do they usually, or like, is it likely that this question will be asked on the Regents?
You know, I haven't seen it in a while, but I worry. I worry about saying, "Oh, you're not going to see that,"
Yeah.
and then, so I mean, it's been on the Regents, and so I worry about it. I can't really say. I can't tell you how likely it is to be there. By the way, the other thing you could do with this is also acceptable. You could do that. The other thing that's also acceptable, if you wanted to, you could do this kind of thing. By the way, that chart should have been on the outside, but sometimes I'm not consistent. I just try to be quick. And you do this as well. They'll also accept that. Okay. Now, again, if it's an ionic compound, you must use brackets. You must use brackets. By the way, they will not do something like this. They will not give you something like this to draw. But I do want to ask you about this type of compound. First of all, what type of compound is it?
There's a polyatomic ion.
Yep.
Ionic.
It's definitely ionic. Okay. And if they ask you what types of bonds are present in this compound, what are you going to say?
Ionic and
There
covalent.
you go. And so if you were asked to draw this electron dot structure, I doubt that you'll see something like this, but if you do, this is really the only thing they would expect you to do. They would expect you to do something like this. So just like before, you put basically the ions in brackets with the charges shown, like that. Now, the actual structure of nitrate is actually this. They don't want you to, you're not expected to know this, don't worry. But this is actually the structure of nitrate. Oops, that's an oxygen. And so if I wanted to be like really thorough, and I wanted the electron dot structure, I would put this inside that bracket like that. But the only reason I show you this is to show you that there's an ionic bond between the copper and the nitrate, but there are covalent bonds within the polyatomic ion. That's why if they ask you what types of bonds are present, you're going to say ionic and covalent. Again, the ionic bond is between the ions, but the covalent bonds are between the atoms in the polyatomic ion, because that's basically a molecular structure, NO3, because it contains only non-metal atoms. Okay. Anything else?
Wait, this is kind of like, okay, so when there are halocarbons, they have to be nonmetals, right?
One more time?
Like with halocarbons, they have to be nonmetals, like the thing that's bonded to.
Okay. Halocarbons are basically.
Is it just the like elements that are on the reference table? Like those are the only ones?
Okay, well let me be clear about what you're asking me. A halocarbon is a modified version of a hydrocarbon. What I have here on the screen, that's a halocarbon. Okay, halo, that refers to halogens. Okay.
Oh, okay.
So that means group 7, group 17. Okay, so that means fluorine, chlorine, bromine, iodine, etc. Right. So if it's a halocarbon, it's a compound that instead of having just hydrogens and carbons, which is what you would have if you had a hydrocarbon, a halocarbon is a modified version of a hydrocarbon. That means it contains at least one halogen atom. So this is this right here is a halocarbon. Okay, so yes, I guess they have to only contain non-metal atoms, but really what's most important is that they only contain carbon, hydrogen, and some kind of halogen atom.
Okay.
Okay. This one, by the way, is called chloroethane. You don't need a one here because there's only one type of chloroethane. I mean, if I put the chloro group, let's say over here on that carbon, that's the same thing as flipping it. So that's not changing it. So chloroethane is the name of that compound.
Wait, this might be like a stupid question, but can metals be bonded to organic compounds, like in general?
The answer is yes, because the only thing that's necessary for a compound to be considered organic is carbon. And so, you know what? I'm going to back up and say, no. I just had one of those moments where I know what the correct answer is, but I know what I want you to walk away thinking. And
Yeah.
and so what I'm going to tell you is that metal atoms. Wait, you asked me if they can be bonded. What type of bond do you mean? Do you mean a covalent?
Just no, I guess not.
Okay, yeah. So then the answer is unequivocally yes. Basically, it can form like a salt, for example. You can have an ion like, let's say, this is acetate. This is an organic compound because it contains carbon. That's really what makes a compound organic. Really, if it contains carbon and hydrogen at least, but this is definitely organic. It's actually acetate. It's the conjugate base of acetic acid. Bottom line is it's definitely organic. But if I have a metal atom like, let's say, sodium ion, these two species will bond ionically, and so what I'm going to get is sodium acetate. And so to answer your question, can they bond? Yeah, you can form an ionic bond.
So then if you were asked to do the electron dot structure for that, it wouldn't be the same as doing it for normal, or like the way that we usually do.
No, if they ask you for the electron dot structure of this, you're going to do just like I showed you before. You're basically going to put the polyatomic ion, the whole thing in brackets like that.
Yeah.
Yeah, it's not going to, you could obviously, since you could in theory know what the structure of acetate is, but they're not really expecting you to know that. I mean, this is actually the structure, but they're really not expecting you to do that. And I don't think they'll ask you that, to be honest with you. They expect you to put that inside there, but
yeah,
that's not going to happen. You don't have to worry about that. We got more people. Good. Anything else?
No, I'm good.
Yeah.
That's really? No. That can't.
Wait, is it not possible to have a review session on Monday?
Well, okay. See, the only problem is I'm actually going to be in school on Monday, and I actually initially had planned to do a review session Monday, but then I forgot that I'm helping the physics department grade their regents.
Oh.
So unfortunately, I'm kind of committed to that. I would love to just tell them, you know what, I can't help you, but I sort of committed without really realizing what I was committed to, and since I told them yes, I guess I have to stick to my guns. But like I said, since I think for the most part this experience has been pretty successful, I think, and that I've been able to ask you and answer a lot of your questions, I will do this again. I will do this again the night before the exam. So like literally, what's that?
When you mean night, are you talking about like mid-afternoon?
Or whenever you guys can be there. I mean, I figured, obviously mid-afternoon is better for me. But if I can get more people to log in, let's say, if we do it at like 7 p.m., Monday night, then I'll do it then.
Okay.
But that's literally, I mean, like that's absolute last minute type of questions. That ought to make you feel really good as far as like going into the exam. You've had a chance to ask as many questions as possible.
Yeah.
But that's but like I said, I'll put that out there. If people want to do it, I hope a lot of people show up. Honestly, because like I said, I think I've been able to ask and answer a lot of questions here. So, anything else? Anything? Any questions?
Can you quickly?
Because by the way, as far as I'm concerned, we're only halfway through this.
Oh my
I have plenty of questions. I actually have questions for you. And by the way, I didn't even get to those questions. I have them all lined up. So
Oh wait, I do have a question.
okay, yep.
Can you quickly go over Le Chatelier's principle?
Absolutely.
One more time?
Absolutely.
Does that give me
Okay, Le
aneurysm?
Chatelier's principle. Okay. All right. So Le Chatelier's principle. First of all, it has to do with equilibrium, number one. And basically, I'm going to explain it in a general way because I think I could use specific examples. In fact, you know what? I'll do that. I'll give you an specific reaction. This is the Haber process. Oops, put the 3 in the wrong spot. And 2.
Mr. Green.
Yeah.
I have to leave, but
Okay.
so the next one is are you gonna like tweet about it?
Yeah. I think the next one will be, like I said, Monday. But if I can get some input as to when most of you can be available, I think that'll give me some idea as to the particular time. But definitely again on Monday. And I think it would be good if you did what you did today by asking a lot of questions. I think
Yeah.
that's very helpful. So come with questions.
Wait, also, Emma wants to know about calculators. Like, I guess what calculators we have to bring for the
Which Emma?
Anderson.
Oh, is she afraid to talk?
I think so.
Okay. Yeah, you need a 4-function.
That's a first.
Did she just talk? Okay. Yeah, you need a 4-function calculator. You need only a 4-function calculator. I cannot promise you that we'll have enough calculators to be able to support everybody. I mean, we might, but I really wouldn't depend on that if I were you. I don't want you guys to have to wait at all before you can do a calculation if you're ready for it. So I would just bring a 4-function calculator. Unfortunately, graphing calculators are not allowed. So you have to bring a 4-function calculator.
All right. Thank you for this, but I'm gonna
Absolutely.
leave now.
Absolutely. I'll see you Monday if you decide to tune in.
Okay.
All right. Take care. Any other questions? I have a Le Chatelier's question here. I'm about to answer it, but was there. By the way, I notice there's more people here. I see Kelly's here as well, but Kelly, if you have a question, you probably want to. You can type it into the chat if you don't want to be on mic. I can unmute your mic if you want me to, or you can unmute it yourself. That's up to you.
No, it's okay. I got it.
Okay. So you're welcome to ask any questions. So I have a Le Chatelier's question here, and the question is, what does it have to do with? First of all, it has to do with equilibrium. And basically what Le Chatelier's principle says is if you apply some kind of a stress to a system at equilibrium, the equilibrium is going to shift in the direction that relieves the stress. And there's basically, I'm going to say 4 different stresses you can apply. And the stresses are changes in concentration. You change concentration, that's 1. If you change temperature, that's another. If you change pressure, that's another stress. And I want to say that's it. That's pretty much it. Basically, concentration, temperature, pressure. There is one other thing that we could talk about with regard to equilibrium, but I'll wait for that. So let's say, for example, I have this system at equilibrium, and let's say I increase the concentration of H2. Okay, So the question is, how's the equilibrium going to change? What's going to happen also to the concentrations of reactants and products after the stress was applied? So let's deal with this one first. What if I increase the concentration of H2? First of all, which way will it shift?
To the left?
Okay, so here's
No,
what,
to the right. To the right.
okay, so yes, it does shift to the right. What you need to remember is that the equilibrium will always shift away from what you increase. It will shift in the opposite direction of what you increase. So if I increase hydrogen, it wants to consume hydrogen to undo the stress that was applied. So if I increase H2, the equilibrium is going to shift to the right. Now, in doing that, something's going to happen to the concentrations of reactants and products. Something's going to happen to the concentration of N2, and something else will happen to the concentration of NH3. So that's my question. If it shifts right, what happens to the concentration of N2?
If it shifts right,
Yeah, if it shifts to the right, going that way, what's going to happen to the concentration of N2? It's going to
decrease.
decrease, absolutely. See, again, if it shifts right, this is always true. If the equilibrium shifts right, to the right, the concentrations of reactants go down, always. Anytime the equilibrium shifts right, the concentrations of the reactants have to go down because they're consumed to make more product because the equilibrium is going to the right. Now, likewise, if the equilibrium is shifting to the right, there's something that happens to the concentration of product. And what happens to the NH3? Anybody?
Oh, sorry. Can you repeat that one more
What
time?
happens to the concentration of NH3
When what?
when the
When
equilibrium
it shifts to the right,
Mm-hmm.
then it would increase.
It would increase. Yeah.
Right. So again, if you increase the concentration of H2, the equilibrium shifts right, the concentration of N2 goes down, the concentration of NH3 goes up. Okay? So that's one possible stress. What if I decrease NH3? What happens? Which way does the equilibrium shift if I decrease NH3?
To the right?
Right.
Exactly. Again, the equilibrium always shifts toward what you decrease and away from what you increase. So if I decrease NH3, it wants to make more of it. So it goes more to the right. So if I decrease NH3, the equilibrium is going to go to the right. And so that means the concentration of H2, what will happen to that?
Decrease?
That's going to go down, absolutely. And the concentration of N2,
Decrease?
that will also decrease, exactly. Okay? Okay. Another possible stress. What if I decrease temperature? What if I decrease temperature? First of all, which way will the equilibrium shift? Number one.
Right.
Okay, it's going to go right.
No. Yeah. Right. Because it's
gonna
like
go right. Yeah, and the reason, again, to figure out which way the equilibrium is going to shift with changes in temperature, you have to ask yourself, where is the heat? The heat's on the right side of the equation. This is an exothermic reaction. So if you decrease temperature, that's sort of like decreasing heat. So again, the equilibrium always shifts toward what you decrease. So if you decrease heat, it wants to make more of it. So it goes to the right. Okay, so the equilibrium is definitely going to go to the right. And so the question then becomes, if it goes more to the right, what happens to the concentration of H2 and N2 and NH3? Oops, come on, N2. All right, let's deal with H2 first. H2, what happens to it if it shifts right?
Decreases?
Yeah, it definitely decreases. If it goes more to the right, H2 decreases. How about N2?
Decreases?
Decreases as well. How about NH3?
Increases?
That definitely increases. Okay? So that's temperature. So we did concentration, we did temperature. What about pressure? This is a little bit, I think, harder to remember, if there is anything that's difficult about this at all. What do you remember about pressure? If you increase pressure,
It has to do with like the moles
absolutely. It has to do with specifically.
of gases. Moles
Okay,
of
good.
gases.
Exactly. That's key. It has to do with moles of gases. So, but what do you remember about which way it shifts? We know it's about gases, but there's something else.
To the side with like the least less amount of moles.
Exactly. So if I increase pressure, EQ is going to shift which way?
It would go to the right.
It's going to go to the right. And again, the reason that it's to the right is because all I'm doing is adding up the number of moles on both sides. So on the reactant side, I have 3 moles of hydrogen plus 1 mole of N2. That basically means I have 4 moles of reactants. Okay. On the product side, I have 2 moles. So again, if you increase pressure, the equilibrium always shifts toward the side that has less moles of a gas. And that means shifting to the right. So what that means is if it shifts to the right, that means N2, the concentration of N2 is going to decrease. The concentration of H2 is going to also decrease. And the concentration of NH3 will increase. Okay? So obviously if I said, if you decrease pressure, all of these answers will be exactly the opposite, because if you decrease pressure, it shifts to the side that has more moles of a gas. So that would mean shift to the left. So that's pretty much it as far as Le Chatelier's principle is concerned. By the way, what if you add a catalyst? What does that do?
It stays the same.
Absolutely, it stays the same. It does not shift. One more thing, actually, now that I'm thinking about this. What if I have something like this? HI, this is a gas. Excuse me, equilibrium, like that. H2, this is a gas as well. And that's a gas as well. Okay. And I say, okay, now I increase pressure. Increase pressure. Which way does it shift?
It stays the same.
It stays the same. Absolutely. Does not shift because, and sometimes they ask this question, basically you have 2 moles of a gas on the reactant side. You also have 1 plus 1 mole of a gas. You have 2 moles on the product side. And since the number of moles on both sides of the equation are the same, if you increase pressure, there's not going to be any shift. There's not going to be a change in the concentration. One more with that. So let's say I had this. So I have CO2 gas in equilibrium with CO2 aqueous. Like that. Okay, now what if I increase pressure? Which way does it shift?
To the right.
Anybody
No,
disagree?
Doesn't it stay the same?
So like an aqueous isn't like a
That's
gas.
an aqueous.
Ah, very good. Yeah, notice that says aqueous. Okay, so if you increase pressure, it's going to shift to the side that has less moles of a gas. So the product side has no moles of a gas. That's aqueous. So that's basically going to drive the equilibrium to the right. Now think about this for a minute. If you increase pressure, what that basically means is that you're increasing the amount of dissolved carbon dioxide. And that's what I said to you about 3 hours ago. If you want more carbon dioxide to dissolve, what you do is you increase the pressure. Remember, gases are most soluble under conditions of high pressure, low temperature. And the reason that they're more soluble under conditions of high pressure is because what you're doing is you're driving the equilibrium toward the side that has more aqueous carbon dioxide, so it's more soluble. So that's pretty much it with Le Chatelier's principle. Anything else? Any other kind of stray questions? I have other questions for you, but any other stray questions, or anything like, things that you don't really remember, that sort of thing? Okay. Well, So now what I have here, I have literally a number of different questions for you, which if you're up for it, we can do them, and we can share out the answers. We'll go as long as you guys can go. Like I said, I have a bottomless pit for this stuff. I'll be here until literally you tell me like, no, there's no more. I don't want to do this anymore. Um, okay, so I have like I said, a number of questions that I have prepared for you, and we'll just do them one by one until you literally puke. By the way, some of you Emma's still muted here. Emma, if you want to participate and you want to type your answers in, there's a little chat bar. Um, just drop that down and type in your answers. I would like you to send me your answers privately. That way you're not influenced by anyone else's answer. Um, so to do that, what you basically need to do is if you look at the chat bar at the bottom where it says to, the default says entire audience, but just send it to me. You scroll down, you'll find it to presenter only, that sort of thing. And then we'll just, like I said, we'll just keep going until you give up. Okay. All right. So first question: number of valence electrons in a calcium atom. Give me your answer. I got 2 correct answers so far.
What group is it in?
What group is it in? You tell me. Well, I mean, if you don't know what group it's in, that's something the periodic table can tell you.
No, that wasn't me. That was my mom. Sorry.
Oh, okay. I'm like, that scared me. That really scared me. Yes, definitely the answer is choice 2. That's because if you look in the periodic table of elements, you'll see that the electron configuration of calcium is 282. Remember, valence electrons are the last electrons in the electron configuration. So clearly, I'm sorry, 2882. Excuse me. That was magnesium I gave you for, but this is calcium 2882. If they ask you for the electron dot structure for calcium, you're going to do this kind of thing, right? Okay, pretty straightforward. All right, let's keep going. Number 2. Which subatomic particles are located in the nucleus of a helium-4 atom? Subatomic particles. Okay, so I got. Okay, so got everybody but Leah. Leah, are you still here?
She's on her phone. I don't think she could like talk.
Oh, she was actually. Well, she can chat. Wow, she's on here by phone. Wow, that's cool. Yeah. Okay, so subatomic particles. I hope you know that subatomic particles are protons, neutrons, or electrons, right? But the key here is that they're in the nucleus. And I hope you know that only particles that are in the nucleus are protons and neutrons, of course. And we should know that in the nucleus of a helium atom, there are 2 protons and 2 neutrons, right? That's what's inside there. So definitely neutrons and protons. Okay, let's keep going. In the late 1800s, experiments using cathode ray tubes led to the discovery of. Unfortunately, I think this is really extraneous stuff. But they do ask you to memorize stuff. If you remember this, I'm impressed. Wow, somebody remembered. Either that or it was a complete guess. I see 2 answers only. Oh, I see another answer. Okay. All right, so what? I'm going to wait a little bit longer. Okay, what you need to remember about this experiment is the cathode ray tube experiment was that experiment where it was J.J. Thomson that he connected a cathode ray tube, which basically an evacuated air tube. Basically, it's a glass tube where the air has been essentially taken out, and there are 2 plates in the inside. And he connected that to an electrical source, like a battery, if you want to say that, like that. And he noticed that for some reason, there was a beam that originated at one electrode and ended at the other electrode. It always seemed to originate from the negative electrode and go toward the positive electrode. And so he reasoned, based on how the direction of the beam, that this beam, whatever it was made of, it must have been negatively charged. And they later found out these were electrons. That's, again, one of those things that you just have to, unfortunately, have to remember. There's another, that's really the only, other than the Rutherford gold foil experiment, the cathode ray tube experiment is the only other experiment that you need to remember, as far as, historical experiments are concerned. So definitely electrons.
Wait, I have a question.
Yep.
What was the gold foil experiment discovering?
Okay. The gold foil experiment was the experiment whereby, thank you for the question, by the way, was a experiment whereby a radioactive source, or particles from a radioactive source, specifically alpha particles, were shot at a thin piece of gold foil. And basically, the takeaway from that experiment is that most of the particles went completely through the gold foil, most of them, like 99% of them maybe. But every so often, a certain number of those particles bounce back. And what they reasoned from that experiment is that there was something inside the nucleus that the alpha particle was striking. Or excuse me, something inside the atom, I should say, that the alpha particle was striking. And what that thing was, of course, was the nucleus. So that was one of the discoveries that came out of the Rutherford gold foil experiment, that there's something called a nucleus, or something that's a center of positive charge and most of the mass of the atom. So you can say it was the experiment that led to the discovery of the nucleus. And also that the nucleus is really, really tiny compared to the size of the atom. And the reasoning from that came from the fact that most of the particles went completely through. That means most of the times it missed this thing that it was striking. And the reason that, because it missed it most of the time, it must have been very small. So the nucleus is really, really tiny. And then the other thing is, most of the atom is empty space. So empty space, that's almost always, by the way, as far as what they ask about the gold foil experiment, the answer almost always has to do something with empty space. Most of the atom consists of empty space. And that's pretty much it as far as experiments are concerned that you have to know. All right, let's keep going. Number 4. The atomic mass of titanium is 47.88 atomic mass units. The atomic mass represents what? I think Leah's gone. I think she tapped out. I always have great satisfaction when kids tap out before I do. I'm satisfied. That's surprising. Okay, definitely all naturally occurring isotopes. You need to remember that different elements have what you call different isotopes. For example, carbon. Carbon has 3 naturally occurring isotopes. Carbon-14, carbon-12, which is the one that we're, most likely, most familiar with, and carbon-13. They're all isotopes because they all contain the same number of protons, but they have a different number of neutrons. And so the question is, if some of the carbon has a mass of 12 and some has a mass of 13, what do you put in the periodic table? You can see that if you average all of these numbers, 12, 13, and 14, you're not going to get 12.0111, which is what's in the periodic table. And so there's something weird going on. First of all, you need to know that atomic masses are only tabulated for the stable naturally occurring isotopes of an element. So carbon-14 is actually radioactive, so it's not included in the average. By the way, I say only the stable isotopes are used unless the element is naturally unstable. Like, for example, uranium doesn't have any stable isotopes, so all of its naturally occurring isotopes are used. But carbon does have stable forms. Carbon-12 and carbon-13 are not radioactive, so these are the only ones that are used. But if you do an average of these two, the average of 12 and 13 is 12.5, and that's not 12.0111. So there's something else going on. It's a weighted average. What you need to know is most of the carbon in nature, 99% in fact, is carbon-12, and only 1% is carbon-13. So they do a weighted average, and it's a weighted average of all of the naturally occurring, again, stable isotopes, if it is stable. So how do you do a weighted average? What you do is you take the abundance, which in this case of carbon is 99, and you multiply that by its isotopic mass, which is 12, plus 1%, actually not percent, but just write it as 1, times 13, and then you divide the whole thing by 100. If you do that, you're going to get something close to 12.0111. I don't happen to know what the abundances of titanium are. Otherwise, I would have done that calculation with you, but that's how it is. It's a weighted average of all the naturally occurring isotopes, not the total mass, not the total mass of protons, neutrons, and electrons. Do I need to explain that? Because not everybody got choice 4. Some of you had a different choice there, but all right, let's keep going. Number 5, which one has the largest atomic radius? Which atom has the largest atomic radius? And I have to say, I don't know what the answer is. I'm not sure of the answer. I wouldn't trust myself to go by the trends, because these elements are not all of them in the same period or the same group. And by the way, even if I knew what the trend was, if I memorized what it was, I wouldn't actually rely on it. And the reason I wouldn't do that is because if I were taking this test, I have 3 hours. And so what I would do is I would simply look in the periodic table, table S, to find out what the atomic radii are. And that's really the best way to handle this question. So I got iron, magnesium, silicon, and zinc. Iron, magnesium, silicon, and zinc. Let's see, iron is where? Where are you? Iron, I don't see you. There we go. Magnesium is here. There. Silicon, where are you, silicon? Atomic number 14. And zinc, atomic number 30. So if I've circled the right ones, and I think I did, looks like magnesium is the answer. So that's what I'd say. Again, sometimes I'll ask you questions where they're all in the same group or period, but if that's the case, then you just use the trends that you learned a while ago, but in this case, it doesn't really apply. How about this one? Which element requires the least amount of energy to remove the most loosely held electron from a gaseous atom? Okay. I see one answer. I see 2. I'll wait some more. 30 seconds. Okay. Well, all right. Well, when you read the words energy required to remove um, the most loosely held electron, what does that mean to you? What does that mean? They're talking about ionization energy.
Electronegativity.
No, not electronegativity. Ionization energy. Ionization energy. Okay. Basically, the nucleus is positively charged because there are protons there, and the electrons are in shells outside the nucleus. Not really, but we'll just say that. And electrons are negatively charged. They're attracted to the nucleus. So it requires energy to remove electrons. The most loosely held electrons are the ones that are in the valence shell. So that's what they're talking about here. They're talking about ionization energy. And so again, I know what the trends are, but since you have 3 hours, I would simply look up the ionization energies of each of these atoms. And I know the answer is sodium, because it's also the most active element. The most active elements are the ones that give up their electrons easily. And so sodium is most likely going to be the one that requires the least amount of energy to remove an electron. So sodium is definitely the answer. All right, let's keep going. Number 7. A balanced equation representing chemical reaction can be written using. Okay, I see 1 correct answer. Let's see 2 correct answers. I think Kelly and Leah bounced. Oh, there you go. Okay, there we go. Okay. Yeah, definitely chemical formulas and coefficients. No question about that. That's kind of an easy question. I'm not going to spend any time going over it. Okay. Number 8. Every water molecule has 2 hydrogen atoms bonded to 1 oxygen atom. The fact supports the concept that elements in a compound are. Okay. I see 2 correct answers. Oh, Leah actually came back. Okay. Okay, yes, the answer is definitely combined in a fixed proportion. Water is always H2O. By the way, compounds, whatever their formulas are, they're always the same no matter where you get them. So carbon dioxide, whether it comes from the tailpipe of a car or from an animal breathing out, the formula is always CO2. Compounds are always made of elements in fixed proportions. That's called the law of definite proportions. All right, let's continue. Number 9, the percent composition by mass of nitrogen and NH4OH is equal to. Okay, you all got that one right. I'm going to assume that you know how to get that. I'm not going to spend any time going over that. So, okay, let's keep going. Which group 15 element exists as diatomic molecules with STP? Okay, so I got 2 correct answers so far. I got 3. Okay, so I'm going to go over this one because not everyone got it right. All the gens and enes are diatomic. So if it ends in gen or ene, it's diatomic. Another way you can remember it is Brinkelhoff. I don't really like that one too much, but it kind of works if you want to memorize that. But this mnemonic device tells you which ones are diatomic. I like gen and ene, so nitrogen is the only one that's diatomic. It exists as N2, not just N. The other ones are monatomic, or they don't exist as diatomic molecules, to say it that way. Let's keep going. Total number of electrons shared in a double bond, double covalent bond. Okay, definitely the answer is 4. I'm not going to spend too much time. A double covalent bond is like that. Each bond is 2 electrons, so that's definitely 4 electrons. Okay. Given the balanced equation representing a reaction, the one you see there, which statement describes the energy change and bonds in the reaction? Okay, definitely the answer is energy is absorbed. The reason I know the answer is that energy is absorbed is because energy is on the reactant side. That means energy is being absorbed. The other thing is, in the reactant, on the reactant side, I have a molecule that consists of 2 bromine atoms that are bonded together. On the product side, they're not bonded together, so that bond was broken. You need to know that any time bonds are made, when bonds are made, anytime, that's an exothermic reaction. Okay? When bonds are broken, on the other hand, that's an endothermic reaction, always. Endo. Okay, let's keep going. Which substance cannot be broken down by a chemical change? Cannot be broken down. Okay, good. Looks like most of you have the answer here. The reason that, of course, the answer is tungsten is because tungsten is the only substance that's an element. These other compounds, these other choices are compounds, and we should know that compounds can be broken down by chemical changes, whereas elements cannot. Let's continue with this. Continue number 14. Okay, so object A at 40 degrees Celsius and object B at 80 degrees Celsius are placed in contact with each other. Which statement describes the heat flow between the two objects? Okay, so heat flows from object. Okay, looks like most of you. Okay, pretty straightforward, right? So I have object A and object B. They're in contact with each other. Object A is at 40 degrees Celsius. Object B is at 80 degrees Celsius, excuse me. And so we know that heat always flows from the thing that's hot to the thing that's cold, or from the thing that's at a higher temperature to the thing at a lower temperature. So definitely heat's going to move from object B to object A. Pretty straightforward. Number 15, which unit can be used to express the concentration of a solution? Okay, I don't see any answers. Oh, okay, here we go. Okay, see 2 answers. Okay, definitely parts per million is the answer. There are only two units that you're going to be asked to express concentration in. One unit's going to be, or could be, mole per liter or molar. The only other concentration unit you'll be asked about is parts per million. And both of those formulas, by the way, how to calculate them, that is, they're both in the reference table. Actually, I want to back up. There is another concentration unit. They could ask you about percent solutions. But all three of these formulas, how to calculate them, they're in the reference table. But that's the only one. Parts per million is the only choice that's you could express the concentration of a solution. And choice one, that's just a distractor. That's liters per second. That's really nothing. I mean, that's just somebody added that choice just to have, four choices. I can't think of what you would, that's maybe that's like rate of flow or something like that. That's definitely not concentration, liters per second. Let's keep going. Number 16, which one's a mixture? Okay, the answer definitely is choice 3. In fact, not only is that a mixture, that's what we call a homogeneous mixture. The reason I know it's a homogeneous mixture is because that says AQ. That's a solution. You need to know that solutions are homogeneous mixtures. The key here, that says aqueous. That means water. This means the solvent here is water. Okay, that means dissolved in water. Which, by the way, if you could zoom in on that solution, right? If you could zoom in that solution, you're not going to find any LiCl. What you're going to find are lithium ions and chloride ions in the solution. And then what you're going to also find, since this is an aqueous solution, is you're going to have water molecules associated around them and oriented toward the ions like so. And again, for the same reason that I've been saying, water is a polar molecule. This is an ion dipole attraction. This is what we talked about a few hours ago. Okay. Which sample has particles with the lowest average kinetic energy? Lowest average kinetic energy. Okay. That's good. I can almost promise you're going to see that question. I'm like 95% sure. Literally, if you see that, you cross it out and you just write temperature. And so basically lowest temperature. Okay. Which gas sample at STP has the same total number of molecules as 2 liters of CO2 at STP? Okay, so for this question, basically, this is Avogadro's hypothesis. And what that basically means is that if you have two different gases at the same T, P, and V, they'll contain the same number of molecules. And so because this says 2 liters of CO2 at STP, the only sample that would contain the same number of molecules at the same temperature and pressure is one that has the same volume. So definitely that choice 2. Okay. Number 19, petroleum can be separated by distillation because hydrocarbons in petroleum have or are. Okay, I see 2 answers. Okay, I see 3 correct answers. I think Leah bounced again. Okay, yeah, definitely different boiling points. The key here is distillation. If you see the words distillation, you need to know that this is a separation technique whereby you separate different liquids in a mixture because they have different boiling points. The idea is that if I have, let's say I have two different liquids, let's say I have a hexane, and let's say decane, right? These are two hydrocarbons, right? This is C6H14, and this is decane is C10H22. And so these two hydrocarbons will have different boiling points. The one that's heavier is always going to be the one with the higher boiling point. So if I boil this mixture of hexane and decane, what's going to happen is first hexane is going to come off, and then after hexane at a higher temperature, the decane will begin to boil, and I can separate them because they have different boiling points. All right, which compound is soluble in water? Insoluble, excuse me. Which one is insoluble? Okay, I see, I think one correct answer. Okay, the answer, okay, good. I see choice, okay. Okay, the answer definitely is choice 4. The reason it's choice 4 is because to answer this question about whether a compound is soluble in water, I have to go to the reference table. And specifically, I need to go to reference table F. See if I can find it. Where are you, reference table F? Keep going. Where are you? Is it here? Yeah, here we go. Okay, so reference table F basically tells you whether a compound is soluble in water or not. And so looking at the choices, one choice says KOH. Now, if you look at the reference table, it says that compounds that contain group 1 ions, which potassium is, it says that these compounds form soluble compounds. So KOH is definitely soluble in water. So that wouldn't be the answer. Continuing, let's see, ammonium chloride. So once again, looking at the reference table, ammonium, it says ammonium always forms soluble compounds. So ammonium anything, ammonium chloride, ammonium nitrate, ammonium bromide, these would be soluble compounds. Sodium phosphate. Sodium phosphate is also not the answer because, once again, sodium is a group 1 ion. So that's definitely going to form a soluble compound. So the only answer would be lead sulfate, because if I look at the reference tables, again, sulfates are normally soluble, right? But if you look at the exceptions, except when combined with calcium, strontium, barium, or lead. Lead is an exception. So lead sulfate would be expected to be insoluble. So that's definitely the answer. All right, number 21. Number 21 says a gas at 25 degrees Celsius and 1 atm. Excuse me, a gas sample is at 25 degrees Celsius and 1 atm, which changes in temperature and pressure will cause the gas to behave more like an ideal gas. So that's one of those things I told you that you're going to have to either understand or memorize. So I see one answer. Let me see, I see 3 correct answers. I don't know if Kelly's still with us. Okay, so definitely the answer is increased temperature and decreased pressure. I could spend time going over that if you want me to, but I did explain that before, so I'm going to move on. Okay, number 22. Isotopes potassium 37 and potassium 42 have the same what? Total number of neutrons, mass number, bright line spectrum, decay mode. Okay, I only see one answer. Okay, see two answers. Okay, the answer definitely is bright line spectrum. Remember that the bright line spectrum of an atom is produced anytime an electron falls from a higher energy level to a lower one. And so every time that electron falls back, it gives off light. And that light that's given off is corresponds to a line in the bright line emission spectrum. Since potassium 37 and potassium 42, they both contain 19 electrons. That means they have the same electron configuration. And if they have the same electron configuration, they should have the same bright line spectrum. They're not going to have the same number of neutrons because potassium 42 actually has more neutrons. Decay mode is also not the correct answer. If you look in table N, you'll see that they actually, if they're both there, they're going to have different decay modes. Mass number is obviously not the answer because you can clearly see they have different mass numbers. And so decay bright line spectrum is the only correct answer for that question. Number 23, which element is present in all organic compounds? Gee, this is really difficult.
Mr. Green, I have to go.
Okay.
All right, thank you.
You're welcome. Which element is present in all organic compounds? Okay, Kelly's logged in her answer. Jesse's got an answer. Okay. Yeah, that's pretty, hopefully easy one. We know that organic compounds must contain carbon by definition, so I don't think there's any reason to explain that. Okay, number 24. Each of the 4 test tubes contain a different concentration of HCl at 25 degrees Celsius. A 1 gram cube of zinc is added to each test tube. In which test tube is the reaction occurring at the fastest rate? So, fastest rate. I think I only see one answer. Okay. Well, the answer is choice 1. The reason the answer is choice 1 is because you need to know that there are a few different things that affect the rate of reaction of reaction. There are factors that affect the rate of reaction, and those things are. Just give me a second, please. I need to. Sorry about that. I just had to speak to one of my children. So yeah, there are different factors that affect the rate of reaction, and Those factors are concentration, pressure, oops, come on, temperature, and the presence of a catalyst or absence of a catalyst. And so what you need to know is that for all of these factors, pretty much if you increase any of them, it's going to increase the rate of reaction. Pressure only has to do with gases, by the way. And so if you increase the concentration, which clearly the first choice has the greatest concentration, that's going to be the one that occurs at the fastest rate. Okay, so that's number 25. Okay, so which energy conversion occurs during the operation of an electrolytic cell? And then there were 3. Definitely electrical to chemical, because this is, oh, wait a minute. This is, yes, absolutely. I just almost misread the question. This is an electrolytic cell. And so what you need to know is an electrolytic cell uses electrical energy to perform a chemical reaction. So that's what they mean by this choice here, electrical energy to chemical energy. Okay, let's keep going. Which compound is an Arrhenius acid? Okay, Kelly's got an answer. Okay, good. Again, Arrhenius acids, the only ones that they're likely to ask you about are the ones that are in the reference table. HCl is definitely an Arrhenius acid because basically, again, when you put it in water, it's going to ionize, ionize into H plus and Cl minus, which is what defines an Arrhenius acid, produces H plus in solution. All right, number 27. Based on the results of testing colorless solutions with indicators, which solution is most acidic? Yeah, that's not an easy question, because I don't know the answer without looking at the reference tables. So, okay, I see one answer. I see 2, 3. Okay, everybody thinks it's methyl orange. And again, without looking at the reference tables myself, I have no idea. So basically what you're going to look for in this question is you're going to look at reference table, the acid-base reference table, which I don't know off the top of my head what it is. Let's see, reference table, where are you? There we go, reference table L, I think. No, M. So the one that's most acidic is the one with the lowest pH. So you guys all think it's methyl orange. So let's see, methyl orange. Oh, let me read that again. Methyl orange, when methyl orange is red. So, okay, so when methyl orange is red, apparently it's at a pH of 3.0, 3.1 and lower. So that's a pretty low pH. Look at the other choices. Solution in which bromethymol blue is blue. Well, I know that's wrong because I know that's at a basic pH. So the pH is going to be greater than 7 here. Oops, greater than 7. Solution in which brome cresol green is blue. Again, I don't know what that is. Brome cresol green is blue at a pH of 5.4 and higher. Yeah, it's looking like the answer. The solution in which phenolphthalein is pink, that's definitely not the answer because that's only going to happen if the pH is 8. So, yep, choice 4 is the answer. All right, let's keep going. Number 28. According to one acid-base theory, Water acts as an acid when water does what? Kelly's logged in. Okay, Emma's in. Emma's afraid to talk. Jesse. Yes, you are. Yeah, choice two is definitely the answer. By the way, one acid-base theory, they're talking about Bronsted-Lowry, but they're not going to call it Bronsted-Lowry, so just be aware of that. They'll call it alternate theory or one acid-base theory. You need to know that acids are proton donors, so that's pretty much the key for that question. Number 29, in which type of reaction is an atom of one element converted to an atom of a different element? And yes, you are afraid to talk. I see 2 correct answers. I see 4. Here we go, transmutation. Yeah, that's definitely the answer. This is an example of transmutation. This happens to be the beta decay of carbon-14. And in this process, you can see that one element, in this case carbon, is being converted to nitrogen, which is the definition of transmutation. This is natural transmutation too. All right, let's keep going. Number 30, which nuclide is listed with its half-life and decay mode? This question is really easy, but I actually don't know the answer because you need to look at the reference table. Okay, I see an answer. One person's got the answer. Or an answer, I should say. I don't know if it's the correct answer. I see 2 answers. Now I see 3. Okay, everybody's saying it's choice 2. And again, I don't memorize decay modes. There's no reason why you need to. But if choice 2 is the answer, nitrogen-16 must have a half-life of 7.2 seconds, and the decay mode must be beta negative. So if I look at the reference table, specifically reference table N, looking for nitrogen-16, and where are you? Nitrogen-16, there you go. So it says 7.13 seconds, and beta negative is the decay mode. So that it's interesting. That says 7.2 seconds. I think it's because this question was given before the reference tables changed, but that's most likely the correct answer. That's close enough to me to think that is just a slight deviation from the reference table. All right, number 31. Atoms X and atom Z are isotopes of which element? I can't tell if I see any changes in the choices. Oh, okay. Now I got some answers. Okay, the answer is definitely carbon. The reason it's carbon is because it says element X and Z both have 6 protons. Again, elements are defined by their protons. The only element with 6 protons is carbon. These happen to be isotopes of each other. This atom X has 6 protons and 6 neutrons. This is carbon-12, of course. And then this element, atom Z, has 6 protons and 7 neutrons. This happens to be carbon-13. So they're isotopes of each other. Okay, let's keep going. 32. Greatest composition by mass of an atom of oxygen 17 is due to the total mass of. Okay, I see 2 correct answers. Okay, the answer is definitely neutrons. What you need to know here is that oxygen 17, oops, come on, has 8 protons and 9 neutrons. And 9 neutrons have more mass than 8 protons, so the greatest composition by mass are definitely the neutrons. Okay, keep going. Number 33, which bond is most polar? Most polar. Okay, I think I see 1 correct answer. Okay, I see 2 answers. Yeah, I can go over this. Yeah, this is a is just an annoyingly simple question. I say annoyingly is because all you need to literally do is to look at the reference table S and look up your electronegativities for each of these atoms. The most polar bond is the bond in which the electronegativity difference is the greatest. And so all you would need to do is literally just look up the electronegativities of each of the elements and figure out which one has the biggest number, or the greatest difference, I should say, between the 2 electronegativities. I actually didn't look at this yet. I suspect the answer is choice 4, only because I know that from top to bottom, electronegativity decreases. So from top to bottom in group 17, the order is fluorine, chlorine, bromine, iodine. And I know that electronegativity decreases going down. And I know that fluorine has the highest electronegativity. And I know that iodine has the lowest electronegativity in group 17. So it's probably, that's choice 4 is probably the answer without actually looking it up. Looking up what the electronegativity of iodine is. I don't know if anybody did that, but I think that's the answer without actually looking it up. But that's all you would need to do. Literally look up the electronegativity values and then
I did.
differences. Okay, so that's probably the answer. That's pretty much it. It's again the bond polarity can be calculated as the difference in electronegativity, right? So if we're dealing, by the way, if we're dealing with 2 non-metal atoms, that's going to be a covalent bond. If we're dealing with a metal and a non-metal, let's say, then that's not going to be a covalent bond because the electronegativity difference between sodium, a metal, and a non-metal is so great that there's no sharing of electrons. This is an electron transfer from the metal to the non-metal. That's going to be an ionic bond. All right, but that's basically all you need to do here is calculate the electronegativity difference. All right, in the formula X2SO3 taken 3 times, the X represents the metal. The metal could be located where? I think you've seen this one before. Okay, I see one correct answer. I see two. I see three. Okay, so clearly in this compound, what you need to know here is that because there's a 3 on the outside of the sulfate, that tells you that this metal atom must have had a charge of +3. The reason I know that is because sulfate has a charge of -2, and the only way that I could end up with this compound is if the ions had these separate charges. And so now you're asking yourself, okay, well, if the metal atom has a charge of +3, what group could that element have come from? And the only group of the choices in which the elements have a +3 charge would be group 13. That's the group with aluminum in it. And aluminum, in fact, does have a +3 charge. So this could be aluminum sulfate, for example. Example of a compound that would have the same general formula. Okay. All right, number 35. At STP, which element is a solid, brittle, and poor conductor of electricity? This is a really okay. That's fine, Leah. Thanks for coming. And then there were how many? 4. I'm gonna win this one, by the way. I'm not gonna tap out before you. Just letting you know. At STP, which element is a solid, brittle, and a poor conductor of electricity? Let's see. 4. Okay. I see choice. I see an answer. I see an answer. I don't know if Emma. Oh, there we go. I was gonna write you off, Emma. I thought you were gone. Is Kelly still here? Okay. I'm gonna go over the answer. If you see the words, you're gonna have to memorize these properties. Unfortunately, this is something else you need to kind of remember. If it's a solid and it's brittle and a poor conductor of electricity, you need to know that that's not a metal, right? Obviously, if it's a poor conductor of electricity, that can't be a metal. If it's not a metal, that means it's a non-metal. Okay, and that's what you're supposed to know from these descriptions, from these physical properties. And so the only non-metal here, well, actually, there's 2 non-metals, right? There's neon and there's sulfur. Now, the reason it's not neon is because you're expected to know that that's a gas. And gases obviously are not solids and they're not brittle. So the answer definitely is sulfur. All right. This is a really good question. Number 36. 1,170 gram sample of sodium chloride completely reacts, producing 460 grams of sodium. What's the total mass of chlorine produced? You probably don't even need a calculator. Okay. Okay, it's 2 answers. I'm just waiting for one more answer. I'll wait like 10 seconds more. Okay, the answer definitely is choice 2. What you need to know here, this is law of conservation of mass. Basically, if you have a 1,170 gram sample of a reactant, then the products that are produced have to have the same mass as the reactant that you started with. That's a law of conservation of mass. So the only mass that would give me, yeah, I can do that. I'll do the types of stoichiometry problems that you're going to see. I'm not going to give you anything too major because you're just not going to see it. But the only mass that satisfies the criterion for the law of conservation of mass is 710 grams of chlorine, because if I add these two masses, again, 460 plus 710, which are the masses of my products, that equals the mass of the reactant that I started with. Okay, so I had a question here about doing stoichiometry questions. I can give you a few examples of the type that you're going to see. We did way more sophisticated problems. There's no reason to do those because you're not going to see it. So I'll just make one up here. So let's see. Let's say I have this reaction. I need to balance it. Okay, so based on this chemical reaction, here's my question. How many, come on, moles of O2 could be produced by the, decomposition, abbreviate, of potassium chlorate? Okay, how many moles of O2 could be produced by the decomposition, DEC period, that means decomposition, of potassium chlorate? So give that a try, see if you can do it. And you know what? This question makes absolutely no sense because there are no numbers in it. Let me just, by the decomposition of, let me just put something in, 3.5 moles, excuse me. That was an easy stoichiometry problem. Easy or really hard. 3.5 moles. You got that? I'm just trying to make this make sense. How many moles of O2 could be produced by the decomposition of 3.5 moles of potassium chlorate? By the way, I just realized that the question that was asked to me to do a stoichiometry question, it was a private question, and I thought you all saw it. I didn't realize it was private. That's why I just skipped. I just jumped off the Regents questions and just jumped into a stoichiometry problem. So do we have an answer? Okay, I see an answer. Don't know if it's right because I just made it up. Probably is. Emma. Okay, so, all right, so the question here is how many moles of O2 could be produced by the decomposition of 3.5 moles of potassium chlorate? So based on the balanced chemical equation, it says if you use 2 moles of potassium chlorate, you're going to get 3 moles of O2. But you don't have 2 moles of potassium chlorate. You have 3.5 moles of potassium chlorate. How many moles of O2 will you get? Well, clearly it's got to be more than 3, right? Because it says if you use 2 moles of this, you're going to get 3 moles of O2. So if I'm using 3.5 moles, it's got to be more than 3. So how do I figure out what that is? what I do is I start with what I'm given. I'm given 3.5 moles of potassium chlorate. I'm going to multiply this by the mole ratio. The mole ratio that I need to consider is the mole ratio between potassium chlorate and oxygen. There's a 2 to 3 mole ratio. So I can either write that as 2 moles of potassium chlorate per 3 moles of oxygen, or I can write it as 3 moles of O2 per 2 moles of potassium chlorate. I'm going to choose the latter. The reason I'm going to choose the 3 moles of O2 per 2 moles of potassium chlorate is because I'm calculating moles of O2, and I need that to be on the top. The other reason, by the way, and this is probably even more important, moles of potassium chlorate won't cancel unless it's on the bottom. So basically, what I'm going to have here is 3.5 times 3 divided by 2. And this looks like 15, no, excuse me. This looks like 10.5 divided by 2. Is that right? Yeah, 10.5 divided by 2. And that looks like 5.25 to me. Okay. Would you like to do another one? Anyone? Bueller? Okay, I'm going to take that as a yeah, yes, no. I'm going to take that as a no. So I'm going to go back to the Regents problems then, unless somebody tells me that they want to do another stoichiometry problem. Okay, so that's that. She just asked Emma. She just asked a question and then just bounced. Okay. All right. How about this one? Given the formula representing a hydrocarbon, which, by the way, before you answer the question, I want you to tell me what this compound is called, because that's kind of a good question. What is that compound called? That's a really good question.
No idea.
Okay. All right. Well, first thing you do is you find the longest carbon-carbon chain. And the longest carbon-carbon chain is either going to be, let's see, 1, 2, 3, 4, or it can be 1, 2, 3, 4. Actually, I think you have to do it this way. You don't have to, actually, but that's one way you can do it, which means if this is your longest carbon-carbon chain, that's a branch. And so this branch is called methyl. And this longest carbon-carbon chain, this class of compounds, or this type of compound, is an alkene because there's a double bond there. And the double bond is in between the first and second carbon. So this is probably one, I'm sorry, back up, name the branch first. This is probably 2-methyl 1 butene. And in thinking about this, you're not going to see anything that sophisticated. So I don't know why. It just seemed like a good question to me when I first thought about it, but you're not going to see anything that difficult. Anyway, the molecular formula and empirical formula for this compound are. So what do you think? What's the empirical and molecular formulas? Okay, I see one answer. I see 2 answers. And just waiting for Jesse. 1, 2, 3, 4, 5. I see 5
I'm
carbons.
stuck between 1 and 3.
Okay.
So.
Okay. Well, okay. Well, let's see here. You see, it can't be choice 3, right? Because if I just count carbons, 1, 2, 3, 4, 5. I have 5 carbons, right? And without even counting the hydrogens, I already know that that's going to be 10 hydrogens because this is an alkene. And the general formula is CnH2n. So that's got to be 10 hydrogens. I mean, I can go back and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the molecular formula, C5H10. The molecular formula can't be C4H8 because, again, there are 5 carbons here. Now, if there were 4 carbons, then that could be the answer. But since there are 5, that's going to be your answer.
So even though there's a branch, like we still include it in the molecular formula.
Absolutely, absolutely. I mean, it's still it's there, right? So you have to include it in the formula, right? Otherwise, how could you know that was there if it wasn't part of the formula? All right,
Yeah.
number 38. Which element forms an ionic compound when it reacts with lithium? I don't know if I just chose an easy Regents exam, but these questions seem really easy. So easy that nobody answered it yet. Oh, finally, here we go. Okay, I see 2 answers, and I'm still waiting for Emma. Okay, so the answer is definitely bromine, because you need to know that ionic compounds are formed with a metal and a non-metal, or at least 2 polyatomic ions, right? So if either of those cases are true, then it's going to be an ionic compound. So so this is the only non-metal that's present, right? So lithium is a metal and bromine is a non-metal. Potassium, iron, and krypton. Krypton actually is a non-metal, but it's a noble gas, so it's unreactive. That's not going to form a compound, basically. Krypton's not going to form compounds. Noble gases generally don't form compounds. That's not entirely true, but that's what they want you to know. All right, number 39. Given the formula representing the molecule shown, the molecule is symmetrical and polar, symmetrical and nonpolar, asymmetrical and polar, asymmetrical and nonpolar. Okay, definitely it has 2 lines of symmetry. So that's definitely a molecule that is symmetrical and nonpolar. And because of that, by the way, if there is another of such molecules nearby, it's going to be attracted to itself by London dispersion forces. Because that's a weak attractive force, this substance here is actually a gas. It's a acetylene gas, or ethine is what you would call it. It's a triple bond, ethine, also known as acetylene. Which compound has both ionic and covalent bonds? I see 1 answer. Okay, good. Yeah, if you see a polyatomic ion in the compound, that compound will always contain ionic and covalent bonds, right? So again, they're not going to ask you for the structure of the compound, but if you were to represent that with an electron dot structure or something like an electron dot structure, you would do something like this. Okay. All right. Number 41, a cylinder with a movable piston contains a sample of a gas with a volume of 6 liters at 293 K, 1 atm. What's the volume of the sample of the gas after it's heated to 303 Kelvin and the pressure is held constant? So I have a cylinder with a piston, gas molecules in there. Oh, why not 2? Okay, I'm sorry. Let me go back. Somebody just asked me about choice 2. Why is that not ionic and covalent? Again, they just keep, you think that's a polyatomic ion. It's not. The reason it's not a polyatomic ion is because the only time OH is a polyatomic ion is if it's bonded to a metal atom. So sodium hydroxide or potassium hydroxide or calcium hydroxide, like that. compound like that, there has to be a metal present. So if you have OH connected to nonmetal atoms, that's an alcohol. That's this. And so this molecule only contains covalent bonds. Alcohols are molecular compounds. They contain nonmetal atoms only. And there are no polyatomic ions here. Right? So don't fall for that trick. I'm telling you, every year they throw that at you, hoping that you fall for it, I think. Really, I guess they're not hoping, but that's really the only reason they would put it there is to, perhaps you'll jump at it and think it's hydroxide, but that's not the answer. All right, back to this one. So you have a gas inside a cylinder, and it's got a volume initially of 6 liters, looks like. And let's see, you heat it up. The temperature here is initially 293 Kelvin, and then you heat this thing up. So now you have a new set of conditions. So now the temperature inside here is 303. And they want to know what the volume is going to be. What's the new volume? Because the pressure is held constant. It's held at 1 atm. So how do you do this? I'll let you work it out before I discuss it. If you have no idea, just say, I have no idea. I'm assuming you're still working. Okay, I see one answer. I see 2 answers. And I don't know what the answer is myself, but we can figure it out. So hopefully you're going to use the ideal gas, the combined gas law, P1 V1 over T1 equals P2 V2 over T2. And since pressure is held constant, we're going to cross it out entirely. And so they're asking you for V2. So we can plug in what we know. We know the initial volume here is 6 liters. And we know the initial temperature here. We know it's 293 K. And the second volume, we don't know what that is. We can call it V2. And the second temperature, I know that that's 303. Now, because the temperature increases, I already know the volume's got to be greater than 6. And so really, now that I'm looking at this, I kind of don't really need to work it out because this temperature here is only slightly bigger than, 303 is only slightly bigger than 293. So the volume is only going to be a little bit bigger. It's not going to be as much as 9. I think the answer is choice 2. And that's, without working it out, that's most likely what the answer is. Number 42. Minimum amount of heat required to completely melt 20 grams of ice at its melting point. Okay, so, okay. I see a question mark there. Okay, so I guess I'll go over it. So the minimum amount of heat required to completely melt. Now, if they ask you to calculate heat, um, more than likely you're going to use one of three possible formulas. There's only three heat formulas that you'll use. Those Q equals mc delta T, Q equals m times H sub F, and then Q equals m times H sub V. And since they're asking you for the heat necessary to melt the sample, you're going to use this one here because fusion, heat of fusion is the heat required to melt um, a substance at its melting point. So since you're talking about water, you're going to use the heat of fusion that's in your reference table. So you're going to use the formula Q equals M, which is the mass, which is 20 grams, times the heat of fusion of water, which is 334 joules per gram. And so I guess without a calculator, you can see that's interesting. Most of you chose choice 2, I think, and I'm not sure why, unless I the wrong. No, that's right, 334 joules per gram. That's definitely the correct constant. I get that. I'm not sure why.
Wait, no, what I did was multiplied the specific heat capacity, which is 4.18 by 20 grams, because it's heat of fusion.
Gotcha.
Oh.
Okay, so, see, that's really nasty. That's really, really nasty that they gave that choice. Let me explain why you're not going to do that. First of all, let's go back to the heating curve. Heating curve looks like this. So you need to remember that at the melting point, which this first plateau represents, the temperature is not changing. And that's the key here. You're melting the ice at its melting point. At the melting point of a substance, and you're talking about water here, the temperature does not change. Its temperature stays at 0 degrees Celsius, right? So if the temperature is not changing, you can't use the formula Q equals mc delta T. The only time you can use Q equals mc delta T is if you see a change in temperature. And there are no temperatures given. So again, if they ask you for the heat necessary to melt a substance and they don't give you any temperature changes, and they can't, right, because at the melting point there is no temperature change, right, you're going to use this formula here. If they ask you for the heat necessary to vaporize a substance, then you'll use the other formula, Q equals M times H sub V. So the answer definitely is choice 3. And I'm glad we did that one, because it'd be a shame to get something like that wrong, because that's not a hard question.
Wait, I'm still confused why it's just choice 3.
Okay. Okay, so the formula, the only heat formula that you can use is this one, right? In other words, I think the one that you were trying to use is Q equals mc delta T, right?
No, I was using heat of fusion, but maybe
Yeah, you just looked at it.
Oh, I don't know why I looked at the specific heat capacity instead of the heat of fusion.
Yeah,
never mind.
That's what happened there. So yeah, 20 times 334 certainly is that number there. Okay, all right, let's keep going. Number 43, temperature of a chemical reaction. As temperature is increased, the rate of reaction increases because, well, why does it increase? Okay, good. I see one correct answer. I don't think Emma's here anymore. I think she snuck away. Okay, the answer definitely is choice 2. There are more effective particle collisions. By the way, effective collisions, there are two things. There are two things that have to be true in order for a collision to be effective. Do you remember what those things are? Two things. If you do, tell me what they are. Just you can write them in or you can unmute your mic and tell me.
You still going?
No idea? Okay. Number one, there has to be the right orientation. That's the first thing that has to be true if a collision is to be considered effective. In other words, the molecules have to collide at the right angle. And the other thing is that they have to collide with enough energy, enough kinetic energy. And so if those two things are in place, if they have the right orientation and enough kinetic energy, that's what you call an effective collision. And so if you increase the temperature, you're increasing the number of molecules with enough kinetic energy. And by the way, the reason that they have to have enough kinetic energy is because they have to overcome the activation energy hill, right? There's that first energy hill that molecules have to overcome in order for the reaction to occur. So if they have enough energy, if they collide with enough energy, that's like giving that ball a really big push up the hill. And so that's basically what you need there. All right, number 44. The entropy of a sample of CO2 increases as the CO2 changes from. Oh, okay. I'm sorry. Somebody's asking me a question. What are the other things that increase collisions? Good question. Let me go back. Let me go back to the question. You guys can't see it because the question was private. So what are the other things that increase collisions? Temperature is one. Pressure is another. But be aware of the fact that if you increase pressure, this only pertains to gases, because what's happening when you increase the pressure on gases, what you're doing is you're decreasing the volume. You're forcing the molecules closer together, and if you do that, they'll collide more frequently. So temperature, pressure, also concentration, right? If you increase concentration, that's going to increase the number of collisions. The reason for that is because if you increase concentration, what you're basically doing is you're putting more molecules in the reaction vessel, right? And more molecules means more collisions, right? So if you have more molecules in the reaction vessel, they're going to collide more frequently. So basically those three things: if you increase the temperature, if you increase the pressure, if you increase concentration, that's pretty much it. That's all you're going to do to increase the number of effective collisions. All right, so that was a good question. Number 44. The entropy of a sample of CO2 increases as the CO2 changes from. Okay, I see one correct answer. Okay. Well, I guess I don't know if the rest of you are unsure about the question, but the word entropy means disorder or randomness. Randomness. So basically, they're asking you in which of the choices is the amount of randomness increasing. Of course, the answer is solid to gas. And that's because if you think of the way the particles are arranged in a solid, they are more or less arranged in an orderly fashion, what is often known as a crystal lattice. But the key is that there's a tremendous amount of order associated with solid crystals. Now, if you change that substance either to a liquid or even more so to a gas, and gas molecules are randomly arranged, right? They're spread far apart, no attractive forces between them. That is the greatest increase in disorder that you can have in any phase change. So that is definitely an increase in entropy. By the way, this process is called sublimation, when you go from a solid to a gas. And there are only two substances that you need to know that do that. Carbon dioxide is the one that you're given in the problem. The other one that you need to know is iodine. Those are the only two compounds, or substances rather, that they will ever ask you about in terms of sublimation. Any solid can, in theory, sublime, but those are the only two that they ever ask about. All right, number 45. Which two factors must be equal when a chemical reaction reaches equilibrium? They must be equal. What must be equal? Okay, good. I see one correct answer. I see two correct answers. Okay, and I don't know if M is still here, but okay. So here's a reaction at equilibrium. This is a general reaction. What you need to know is that in equilibrium, the forward reaction is occurring and the reverse reaction is occurring, and the rates are exactly the same. That's by definition what an equilibrium is. The concentrations don't have to be the same. In fact, usually they're not. They're almost never the same, but the rate of the forward reaction, basically how fast A and B react to produce C and D, is equal to the reverse reaction, or in other words, how fast C and D react to produce A and B. The forward and reverse reactions have to be equal. Okay? All right, so that's that. Number 46. Which one represents an unsaturated hydrocarbon? Which one is unsaturated? Okay. So unsaturated. Unsaturated means, first of all, it means there's a double or triple bond there. That means alkene or alkyne. Okay. And basically, if you know what the general formulas are of alkanes, alkenes, and alkynes, you can figure out which compound is which. So here are the general formulas for each type of hydrocarbon. CnH2n minus 2. Okay, so we just need to figure out which one, and by the way, this is alkane. Oops, come on, alkane. This is ene. Just going to abbreviate to save a little time. This is alkyne. So we need to figure out which one of these formulas represents either an alkene or alkyne. I know it's not that. I know it's not choice 1 because that's an alkane. I know that because it conforms to the general formula Cn2n minus 2. I also know that choice 2 is not the answer because that's also an alkane. Again, it conforms to that general formula. C8H14 and C7H16. Well, C7H16, that's also an alkane, right? So that can't be the answer. The answer is this. This is C8H14. And this is an alkyne, actually, because, again, if I figure out, what this, I'm sorry, I'm just struggling with how to explain this. If I use an N of 8, in other words, if there are 8 carbons, the number of hydrogens that I would have here would be 14 because 2 times 8 minus 2 is clearly 14, which means that this compound has a triple bond in it. So basically 8 carbons, but there's at least one triple bond. 1, 2, 3, 4, 5, 6, 7, 8. The rest of these are hydrogens. Like that. 1, 2, 3, 4, 5, 6, 7, 8. This actually is octine. Octine. Okay? All right, so that's number 46. And then there were 2. I'm going to win. The reaction between an organic acid and an alcohol produces. Any idea? I don't know if that's. I don't know if that's a. Okay. I see an answer there. Yeah, the answer is ester. That's just something you're going to have to, that's just one of those things you're going to have to memorize. Unfortunately, there are some things you have to just flat out memorize, and that's this reaction between an organic acid and an alcohol. That's esterification. Esterification. And again, there's no way around memorizing some stuff, and in organic chemistry, that's what you're going to have to memorize. So an ester is the answer. Number 48. Which balance equation represents a redox reaction? Okay, Kelly, you're welcome. And then there was one. So just me and you, Jesse. We'll stop at 50. How about that?
Okay.
I got to tell you, I admire your stamina, kid, because I'm telling you, I don't think I would have done it.
Yeah.
I think
I'm
you're trying to
surprised.
I think you're trying to get 200s. That's good though.
Yeah, that's the goal.
Okay.
Hold up. I'm just like staring at this right now. I I think I'm like right now kind of in between one and no, not one, two. Oh, is it? Shh. Sorry, my sister.
Hmm.
2 and the 4 right now.
Okay. Well, I would agree with you that it's definitely one of those. But I think you should kind of lean towards one obvious, like one that's more obvious.
The 2?
Okay. Well,
No, 4.
yeah, it's definitely 4.
4.
And the reason it's 4 is because, first of all, 4 is a single replacement reaction. Number one, single replacement reactions are always redox. The other thing that should be obvious is that anytime you have a change in oxidation number, that's automatically a redox reaction. The reason I say it should be obvious is because magnesium is all by itself here, and it has an oxidation number of 0. But here it's in compound form, which means it can't be an oxidation number of 0. In fact, it's +2. So I know there's a change in oxidation number. If you find 1, you're going to find 2. So basically, that's really the only answer it could possibly be. So definitely
Yeah.
choice 4. Um, number 49.
Two has an. Oh, 1.
Okay. So it says a solution with a pH of 2 has a hydronium ion concentration 10 times greater than a solution with a pH of, you said, what'd you say? 1?
1.
1. Okay.
Yeah.
So the question is, what's the H plus ion concentration of a solution with a pH of 1?
1.0 times 10. So 10.
Okay. Well, okay. So if the pH is 1 and you want to know what the H plus ion concentration is, basically what you do is you take the pH and you negate it and raise it to a base of 10. So the H plus ion concentration here is 10 to the minus 1. Okay.
Oh,
Now the pH is 2. I think a lot of people might miss this question. This is kind of a difficult one to struggle with. If the pH is 2, the H plus ion concentration is 10 to the minus 2. So the question is, which number is bigger, this one or this one?
1.
Yeah.
Or, yeah, -1.
Yeah, this one is obviously bigger, right? So the question here says a pH solution with a pH of 3 has a hydronium ion concentration that's 10 times greater. Now, if you're saying it's choice 1, well, that can't be right because 10 to the minus 1 is actually bigger than 10 to the minus 2.
Yeah.
So And so there.
Yeah, that makes sense.
And so
Also because 3.0 is like, or 2.0 is more acidic than
yeah,
3.0.
exactly.
So
Exactly.
just
So
realized.
again, if the pH is 3, right, then that means the H plus ion concentration is 10 to the minus 3, which means that in fact the solution with a pH of 2, oops, minus 3, excuse me, this is actually 10 times greater than that. So that, yeah, so choice 3 would actually be the answer.
Yeah.
I don't know pretty much how else to go over that one, but I think you should try more of those questions. And the last one, which isotope is used to treat cancer?
All right, hold on. Let's see if we talked about it like a couple of hours ago. Okay, so I think cobalt 60.
Absolutely. That's it. That's the only, again, they will ask you about these other ones, but cobalt 60 is the only one that's going to treat cancer.
Okay.
All right. The rest of these are part 2 questions. If you want, you can try those yourself, and in the next review, if I get a chance to do another one, you can bring them up. But I strongly recommend that if you come again, that you have questions to begin with, because I think that first little bit of review was really effective because I was able to answer like things that you know you have difficulty with. So,
Yeah.
all right. And like I said, I appreciate your stamina because I'm telling you, 4 hours is a marathon.
Yeah, well, thank you for doing this.
Yeah, no problem. No problem at all. Just do me a favor, if you can try to get more people.
Yeah, see, what happened is yesterday were a couple of people's birthdays, actually,
Oh,
so there were some
okay.
celebrations going on.
Oh, I see.
So that's probably why.
Okay, all right. It's all good. All
So
right.
hopefully next time, more
All right.
people.
Very good. Again, thanks for coming, and good luck on your exam if I don't see you before then.
All right.
All right, take
Bye.
care.
How do I leave?